In October 2022, 3 physicists won the Nobel Prize for proving something that shouldn't be possible, not at light speed, instantly. They showed that 2 particles, separated by any distance, city blocks or galaxies, can influence each other instantaneously. Einstein spent 30 years trying to prove this was impossible, calling it spooky action at a distance. He died believing the experiments would vindicate him. They didn't. Today, quantum entanglement isn't just real, it's the foundation of quantum computers, unhackable communication networks, and experiments that violate every intuition you have about cause and effect. Change one particle here, and its partner responds across the universe before light could possibly travel between them. But to understand why this discovery shattered physics, we need to go back to a world where atoms were still a theory. In 1899, if you knew the position and velocity of every particle in the universe, you could calculate the future perfectly. Newton's laws governed the planets, Maxwell's equations explained light, and thermodynamics predicted heat flow with clockwork precision. The cosmos was a machine. Lord Kelvin told students there was nothing left to discover in physics except better measurements. Scientists calculated planetary orbits centuries in advance. They predicted eclipses to the second. Even the newly discovered electron obeyed strict deterministic rules as it orbited atoms like a tiny planet. Causality was absolute. Every effect had a prior cause. Information traveled at finite speeds through space. Objects had definite positions and velocities whether you measured them or not. Reality existed independent of observation, solid and knowable. Then, in 1900, a German physicist noticed something in the light from hot metal that made no sense. Max Planck was studying blackbody radiation, the glow from heated objects. Classical physics predicted that hot metal should emit infinite energy at ultraviolet wavelengths. It was called the ultraviolet catastrophe, and it was spectacularly wrong. Real ovens didn't vaporize the universe. Planck found a solution by introducing a constant 6.626 times 10⁻³ joule-seconds that forced energy to come in discrete packets. Light wasn't a smooth wave. It was granular, like atoms. An electron jumping between orbits couldn't release any amount of energy, only specific chunks determined by Planck's constant times frequency. He thought it was a mathematical trick, not reality, but the implications spread. If energy has a smallest unit, then change itself is discontinuous. An electron doesn't slide between states. It vanishes from one orbit and appears in another with nothing in between, no journey, no cause. But the real horror was still hidden in the math, waiting for someone to ask what happens between measurements. In 1905, Einstein solved it, not by fixing Planck's math, but by taking it seriously. Light wasn't just acting like it came in packets. It actually did come in packets. Discrete bullets of energy he called photons. He used this to explain the photoelectric effect, where light knocks electrons off metal. Classical waves should accumulate energy gradually, but the electrons fly off instantly when you hit a threshold frequency. The energy arrives in chunks, 6.63 times 10⁻34 joule-seconds at a time. Planck's constant made real. But now physics had a problem. Light diffracted through slits like a wave. It also punched electrons like a particle. Same phenomenon, 2 mutually exclusive descriptions. You couldn't say which one was true because experiments proved both were. The math worked. Reality didn't add up. Within 2 decades, a young physicist would discover something far worse lurking inside the atom. Niels Bohr published his atomic model in 1913. Electrons orbit the nucleus, but only at specific distances, fixed energy levels like rungs on a ladder. An electron, in the n=2 shell, sits exactly 2.12 times 10⁻10 meters from a hydrogen nucleus. Never 2.13, never in between. When an electron absorbs a photon, it jumps to a higher rung. When it drops back down, it emits light at a precise wavelength. That's why hydrogen glows at 656 nanometers, that signature red line in every spectroscope. The math predicted every wavelength perfectly. But the jump itself made no sense. The electron doesn't accelerate from one orbit to another. It disappears from the lower level and reappears at the higher one instantaneously, with no trajectory, no time elapsed. Bohr called it a quantum leap, and he had no explanation for how it happened. Particles were teleporting inside every atom in your body, billions of times per second. But here's the detail that everyone missed at the time. Werner Heisenberg published his uncertainty principle in 1927. You cannot measure an electron's position and momentum at the same time. Not because your instruments aren't good enough, because the electron doesn't have both properties simultaneously. The math is absolute. If you pin down position to within delta x meters, momentum becomes uncertain by at least h4 pi delta x. Titan 1, the other blurs. At the Planck scale, 1.6 times 10 minus 35 meters, the uncertainty becomes infinite. Position and momentum are conjugate variables, locked in opposition by the structure of quantum mechanics itself. Before you measure, the particle exists in a superposition, a cloud of probabilities described by a wave function. The act of measurement collapses that cloud into a single outcome. Reality doesn't exist until you look. Cause and effect require objects to have definite properties that evolve predictably. Heisenberg had just proven they don't. Einstein immediately recognized this as an existential threat to causality itself. Einstein wrote a letter to his friend Max Born, the line that survived history: God does not play dice with the universe. He meant it literally. If quantum mechanics was right, particles had no definite properties until something measured them. But what qualified as a measurement? Does a photon hitting a detector count? Does the detector need a conscious observer reading the result? The math worked perfectly, but the philosophy underneath was collapsing into absurdity. Bohr defended the Copenhagen interpretation. Particles are probability clouds. Measurement collapses the wave function, asking what happens before measurement is meaningless. Einstein refused to accept it. Reality can't depend on whether someone's looking. The debate split physics into two camps: the pragmatists who used the equations without asking why they worked, and the realists who insisted there had to be something deeper. Conferences turned hostile. Papers got personal. By the early 1930s, Einstein was isolated, teaching at Princeton while Bohr's interpretation dominated Europe. Most physicists moved on. The theory predicted everything correctly. Shut up and calculate became the unofficial motto. But Einstein wasn't done. He was about to weaponize entanglement against quantum theory. In 1935, Einstein co-authored a paper with Boris Podolsky and Nathan Rosen. The EPR paper, as it became known, presented a thought experiment designed to prove quantum mechanics was incomplete. Take two particles that interact, then fly apart in opposite directions. Quantum mechanics says they're entangled. A single wave function describes both. Now measure the first particle's spin. Instantly, you know the second particle's spin, even if it's on the other side of the galaxy. But here's Einstein's trap. Either the second particle always had that spin value, meaning quantum mechanics is incomplete because it can't tell you what it was, or measuring the first particle somehow affected the second one faster than light. Einstein called this spooky action at a distance, and he meant it as mockery. Option 1 meant hidden variables existed that quantum theory couldn't see. Option 2 violated relativity. Nothing travels faster than light, including information. Either way, something was wrong. Bohr's response was maddeningly vague. The particles aren't separate objects, they're part of a unified system. Measurement doesn't send a signal. Einstein wasn't satisfied, but he had no experimental test to settle it. The distances involved were too vast, the measurements too precise, the technology didn't exist. For 30 years, it remained a philosophical curiosity with no way to test it. John Bell was a physicist at CERN, working on particle accelerators by day and obsessing over the EPR paradox at night. In 1964, he published a 4-page paper that changed everything. Bell derived a mathematical inequality, a threshold that any theory based on local hidden variables had to obey. The setup was elegant. Take entangled particles, measure them at different angles, repeat thousands of times. If Einstein was right and particles carried hidden instructions, the correlation between measurements couldn't exceed a specific value. Quantum mechanics predicted correlations that violated Bell's inequality, not by a little, by a lot. The inequality forced a choice. Either locality is real and particles can't influence each other faster than light, which means hidden variables and quantum mechanics is wrong, or realism is real and particles have definite properties before measurement, which also means quantum mechanics is wrong. Bell proved you can't have both and match quantum predictions. Physicists finally had a test. The math was ironclad, the experiment was theoretically possible, someone just had to build it. Bell had turned philosophy into physics. The real question is what would happen when someone actually ran the experiment. In 1982, a French physicist named Alain Aspect finally built the machine. He used calcium atoms excited by lasers to spit out pairs of entangled photons, then sent them flying in opposite directions toward polarization detectors 12 meters apart. The trick was switching the detector settings while the photons were mid-flight, faster than light could cross the gap. If Einstein was right, if hidden variables controlled everything, the photons couldn't possibly coordinate their spins in time. The results came in over months of running the experiment. Quantum mechanics predicted a correlation value above 2. Local realism predicted it had to stay below 2. Aspect's photons hit 2.697, plus or minus 0.015. The universe wasn't playing by Einstein's rules. Locality was dead, or realism was dead, or both were dead. But physicists weren't ready to accept what this meant for the fabric of spacetime. The skeptics didn't surrender quietly. They found gaps in Aspect's setup, loopholes that could maybe, possibly explain away the results without breaking reality. The detection loophole was first. Only 10% of photons actually got measured. Maybe the missing 90% were hiding Einstein's variables. Then came the locality loophole. Were the detectors truly switching fast enough? And the freedom of choice loophole. What if the universe was pre-selecting which measurements to make? A cosmic conspiracy rigging the dice. Each hole demanded a new experiment. Anton Zeilinger closed the detection gap in 1998. Nicholas Giesen stretched the distance to 18 kilometers in 2000. By 2015, 3 separate teams closed all major loopholes simultaneously, using everything from superconducting detectors to random number generators seeded by light from distant quasars billions of years old. The universe kept violating Bell's inequality. Einstein's dream was officially over. Meanwhile, a darker interpretation was gaining traction in the quantum foundations community. Hugh Everett proposed it in 1957, and his PhD advisor hated it so much, Everett left physics entirely. The many worlds interpretation says wave function collapse isn't real. When you measure a particle, you don't force it to pick a state, the universe splits. One branch gets spin up, another gets spin down. Both versions of you now exist, each seeing a definite outcome. Entanglement just means those splits are correlated across space. When you measure one photon and get vertical polarization, there's a version of you 12 meters away, measuring horizontal, and another version measuring vertical, branching endlessly. Everett's math worked perfectly, no collapse needed, but the cost was everything. Every quantum event, every particle interaction, every measurement in the universe spawns countless copies of reality, an infinite tree growing new branches trillions of times per second. You're not one person, you're a smear of consciousness across incomprehensibly many parallel timelines, and they're all equally real. But if every possibility exists, what does terrifying even mean anymore? In 1978, physicist John Wheeler proposed something that should be impossible. Send a single photon toward a double slit, but don't decide how you're going to measure it until after it's already passed through. Will it behave like a wave that went through both slits or a particle that picked one? The answer depends entirely on your choice. If you measure which slit it went through, you'll find it took one path, like a particle. If you let it interfere with itself, it acts like it went through both, like a wave. The photon's past conforms to your future decision. Experiments in 2007 confirmed it using light from distant quasars, photons that had been traveling for billions of years. The measurement you make today reaches backward across cosmic time and dictates what that photon was doing before Earth even existed. Causality doesn't just bend, it runs in reverse. Then quantum information theorists discovered something even more unsettling about what entanglement allows. In 1993, Charles Bennett and his team at IBM proved you could transmit a quantum state across space without ever moving the particle itself. The protocol requires 3 qubits, the one you want to send, an entangled pair shared between sender and receiver, and 2 bits of classical information sent through normal channels. You perform a joint measurement on the original qubit and 1/2 of the entangled pair. That measurement collapses both, destroying the original state completely. You send the measurement result to the receiver, who uses it to transform their half of the entangled pair into an exact replica of what you started with. The first experimental demonstration happened in 1997 across a lab bench in Innsbruck. By 2017, China's Mikyus satellite teleported photon states across 1,400 kilometers of open space. The original is always annihilated. The copy appears elsewhere. It's not transportation, it's destruction and reconstruction. But here's the detail that everyone missed at the time. In 1982, William Wouters and Wojciech Zurek proved something called the no-cloning theorem. You cannot make an identical copy of an unknown quantum state, period. If you try to measure it to learn what it is, the measurement collapses it and you lose the original information. If you don't measure it, you have nothing to copy. This isn't a technological limitation, it's written into the math of quantum mechanics itself. Classical information can be copied infinitely with no degradation. Quantum information is different. It's fragile in a way that has no classical analog. You can move it, you can transform it, but you cannot duplicate it. That's why quantum teleportation works. The original gets destroyed, so no clone ever exists. It's also why quantum cryptography is theoretically unbreakable. If an eavesdropper tries to copy the quantum key, the attempt itself leaves detectable traces. Some knowledge cannot be stolen because it cannot be replicated. This would become weaponized in the race for quantum computing. Schrödinger didn't believe any of this. In 1935, he proposed a thought experiment to show how absurd quantum mechanics had become. You put a cat in a box with a vial of poison triggered by a radioactive atom. The atom is in superposition, decayed and not decayed, so the cat must be both alive and dead until you open the box. He meant it as a joke, a proof that the Copenhagen interpretation led to nonsense. But the joke became the most famous metaphor in physics, because if entanglement is real, if measurement creates reality, then the cat genuinely exists in both states, not as a figure of speech, as a physical fact encoded in the wave function. The math doesn't distinguish between electrons and cats. Superposition applies at every scale unless something forces a collapse. But we never see macroscopic superpositions in daily life. No half-dead cats, no chairs in 2 places at once. The real question is at what scale superposition collapses, and whether it ever does. In the 1980s, Wojciech Zurek proposed an answer that didn't require consciousness or hidden variables. Decoherence. A quantum system isn't truly isolated. It interacts constantly with its environment. Air molecules, photons, thermal vibrations. Each interaction entangles the system with trillions of environmental particles. That entanglement spreads the superposition outward until it's diluted into the environment, effectively irreversible. The wave function doesn't collapse. It just becomes so hopelessly scrambled that interference terms vanish. Classical behavior emerges not because observation is special, but because isolation is nearly impossible at large scales. A dust grain decoheres in 10⁻31 seconds. A human in 10⁻26 seconds. Schrödinger's cat never stays quantum long enough to open the box. Decoherence explained why we don't see everyday superpositions without invoking magic. It gave physics a boundary between quantum and classical that arose naturally from the equations. But decoherence wasn't fast enough to explain everything physicists were observing. In 1977, George Sudarshan and Baidyanath Misra proved something stranger. If you measure a quantum system continuously, you freeze its evolution entirely. A radioactive atom that should decay in 1 second will never decay if you check it every microsecond. The act of observation pins the wave function in place. It's called the quantum Zeno effect, after the Greek philosopher who claimed motion was impossible. Physicists thought it was a mathematical curiosity until 1990, when Wayne Itano's team at NIST trapped 5,000 beryllium ions and hit them with laser pulses. Continuous measurement suppressed their quantum transitions by 96%. A watched quantum pot literally never boils. The implications are unsettling. Observation isn't passive recording. It's an active force that reshapes probability itself. In 2015, researchers at Cornell demonstrated the inverse. Rare measurements can accelerate decay instead of freezing it. Reality responds to how often you look and in what way. Timelines bend under the weight of attention. Meanwhile, engineers were building machines that exploit entanglement for computation. A classical bit is binary. It's 0 or 1, on or off, there or not there. A qubit is both at once, suspended in superposition until you measure it. Two entangled qubits don't just hold 2 states, they hold 4 simultaneously. 3 qubits hold 8. 10 qubits hold 1024. The scaling is exponential. A 300-qubit machine, if you could build one, would represent more states than there are atoms in the observable universe. 2 to the 300th power is a number with 91 digits. That's not just faster computing, it's a different kind of computing entirely, where every possible answer exists in parallel until the system collapses to one. But entanglement wasn't cooperating. It was decohering faster than anyone predicted. The problem wasn't theory, it was time. Qubits lose coherence within microseconds, sometimes nanoseconds, as stray photons or thermal vibrations leak information into the environment. IBM's early machines kept entanglement alive for 90 microseconds. Google stretched it to 120. That's not long enough to factor a 10-digit number, let alone crack RSA encryption. Worse, every qubit you add makes the system exponentially more fragile. 5 qubits might stay coherent for 100 microseconds. 50 qubits collapse in 10. Scaling wasn't a linear engineering challenge, it was a cliff. Teams tried cryogenic cooling to near absolute zero, magnetic shielding, vacuum chambers. The entanglement still bled away. By 2018, most physicists believed practical quantum computing was decades out, maybe centuries. Then, in 2019, Google announced they'd achieved something impossible. The Sycamore processor had 53 qubits. Google gave it a single task: sample the output of a random quantum circuit, a calculation with no real-world use. Sycamore finished in 200 seconds. IBM's Summit supercomputer, the most powerful classical machine on Earth at the time, would need 10,000 years to do the same calculation. IBM contested the claim, said they could do it in 2.5 days with better algorithms. Google revised down to 600 years. The exact number didn't matter. Quantum supremacy, the moment a quantum computer outperforms any classical system, had arrived. The calculation was useless, but the proof wasn't. Within a year, China's Zhuzhang processor solved a photon sampling problem in 200 seconds that would take the fastest supercomputer 2.5 billion years. The gap was widening. But here's the detail that everyone missed at the time. Nobody could independently verify the answer. When a quantum computer solves a problem that would take a classical machine billions of years, there's no way to check if it's right. You can't simulate the quantum calculation on classical hardware because that's the whole point. You've built a machine whose outputs outpace verification. In 2020, researchers at USTC admitted their photon sampling results couldn't be validated by any existing system. They published statistical tests, cross-checks against smaller problems, but the core output remained a black box. The quantum computer said the answer was X. You either trusted the entanglement or you didn't. This isn't a bug. It's entanglement creating computational states that collapse before you can audit them. The superposition does the work. The measurement destroys the evidence. You're left holding a result with no classical path to reproduce it. And cryptographers realized this power could break the encryption protecting civilization. In 1994, Peter Shor published an algorithm that factored large numbers exponentially faster than any classical method. RSA encryption, the foundation of secure communication, relies on the fact that multiplying two primes is easy, but factoring the product is computationally impossible. A 2048-bit key would take a classical computer longer than the age of the universe to crack. Shor's algorithm does it in hours. It uses quantum superposition to test every possible factor simultaneously, and entanglement to correlate the results. The calculation collapses into the prime factors with near certainty. Every bank transaction, every military communication, every state secret protected by public key cryptography becomes readable. The NSA issued a memo in 2015 urging all agencies to transition to post-quantum encryption. China announced a $10 billion quantum initiative the same year. Nobody's built a quantum computer large enough to run Shor's algorithm against real-world RSA yet, but the math is sound. The countdown started the moment the paper was published. The real question is whether quantum cryptography can defend against quantum attacks. Quantum key distribution uses entangled photons to generate encryption keys that are physically unbreakable. You send Alice one photon from an entangled pair, Bob gets the other. They measure their photons and share the results. Because entanglement correlates the outcomes, they end up with identical random keys. No information travels between them. The key materializes from collapse. Here's the defense. Any eavesdropper trying to intercept the photons has to measure them, and measurement destroys the entanglement. The quantum state collapses differently. Alice and Bob's keys stop matching. The intrusion reveals itself in the statistics before a single secure message is sent. You can't hack a channel that self-destructs under observation. In 2016, China launched the Mikyus satellite and demonstrated quantum key distribution across 1,200 kilometers. They transmitted entangled photons from orbit to ground stations in Beijing and Vienna, then held a quantum-encrypted video call. The first communication secured by particles that had never been in the same location. By 2021, China had a 2,000 kilometers quantum network linking banks and government offices. But entanglement wasn't just threatening security, it was threatening space-time itself. In 2013, Juan Maldacena and Leonard Susskind published a paper with 3 letters that rewrote physics: E-R-E-P-R. Einstein-Rosen bridges, the wormholes predicted by general relativity in 1935, and Einstein-Podolsky-Rosen pairs, the entangled particles that same year, weren't separate phenomena. They were identical. Every pair of entangled particles is connected by a microscopic wormhole threading through space-time. When you measure one particle and its partner responds instantly 10 kilometers away, information isn't traveling through space. It's taking a shortcut through the geometry itself. The math worked. Entanglement entropy, the measure of quantum correlation, matched exactly the surface area of the wormhole throat predicted by Einstein's equations. Two independent theories, separated by decades, describe the same structure from different angles. If true, this would mean space-time itself is woven from entanglement. Gerard Hooft discovered it in 1993 while studying black holes. Leonard Susskind refined it into a full theory. The holographic principle says our 3D universe is a projection, like a hologram, encoded on a 2D surface at the edge of space-time. Every particle, every force, every event in a volume of space can be perfectly described by information stored on its boundary. A sphere containing a galaxy holds no more information than its surface area measured in Planck units, roughly 1070 bits per square meter. Entanglement became the stitching. When particles entangle, they create connections in the boundary that manifest as geometry in the bulk. The fabric of space emerges from quantum correlations, the way a photograph emerges from interference patterns in laser light. But physicists weren't ready to accept what this meant for black holes. Stephen Hawking proved in 1974 that black holes radiate, leaking particles until they evaporate completely. The radiation looked thermal, random, carrying no trace of what fell in. A star, a library, a hard drive, all reduced to the same featureless glow. Quantum mechanics forbids information destruction. If you burn a book, the information survives in the smoke and ash, encoded in particle states. But Hawking radiation seemed to erase it permanently. Two particles entangled outside the event horizon, one falls in, the other escapes as radiation. The entanglement breaks. For 40 years, no one could reconcile it. Either general relativity was wrong and black holes don't work as Einstein predicted, or quantum mechanics was wrong and information can vanish. Every solution created new paradoxes, firewalls at the horizon that incinerate anything approaching, remnants that violate thermodynamics. Then Hawking made a stunning concession that changed everything. July 2004, a packed auditorium in Dublin. Stephen Hawking steps to the podium and does something physicists never do. He admits he was wrong. For 30 years, he'd argued that black holes destroy information, that the universe is fundamentally lossy. Now he reversed himself completely. Black holes preserve every bit of information that falls in, encoded in the quantum correlations of the Hawking radiation streaming out. The entanglement survives. A particle falling past the event horizon remains quantum-linked to its partner in the radiation. The information doesn't vanish into some inaccessible interior. It's written on the surface, in the subtle patterns of outgoing photons and gravitons. Hawking paid John Preskill a baseball encyclopedia. The bet was settled. Physicists breathed easier. The paradox was solved. But here's the detail that everyone missed at the time. 2012, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully publish a 4-page paper that reopens the wound. They find something hiding in Hawking's solution. If information escapes in the radiation, entanglement must connect the outgoing particles to the infalling ones. But that same infalling matter is already entangled with the black hole's interior. Now you have one system entangled with two partners simultaneously. Quantum mechanics forbids this. The math forces a choice. Preserve the information and you break Einstein's equivalence principle. The event horizon becomes a wall of high-energy particles, a firewall at 1032 Kelvin that incinerates anything approaching. Freefall through empty space becomes fatal. Or preserve equivalence and information is destroyed after all. There's no middle ground. Black holes are either killers at the threshold or they erase reality itself. And this paradox revealed something deeper about the nature of entanglement itself. The firewall paradox exposes a hard limit built into quantum mechanics. A particle can be maximally entangled with exactly one partner, not two, not a diffuse cloud, one. If particle A shares perfect entanglement with particle B, it has zero entanglement budget left for particle C. This is monogamy. It's not a metaphor. It's a theorem proven in 1999 by Charles Bennett with ironclad math. The firewall paradox violates monogamy. The outgoing radiation can't be entangled with both the infalling matter and the black hole's interior. One bond must break. Information must choose a single path. And suddenly physicists had a new tool. Monogamy constrains how quantum correlations can be distributed across space, across time, across event horizons. It sets boundaries on what the universe can remember and where it can hide that memory. But entanglement monogamy wasn't just a curiosity, it was a weapon. In 2003, physicist Wojciech Zurek asked a different question. If quantum superpositions are everywhere, why do we only see one outcome? His answer was brutal: quantum natural selection. States that entangle most aggressively with their environment reproduce copies of themselves into photons, air molecules, radiation. Fragile superpositions die immediately, buried in decoherence. What we call classical reality is just the states that survived. A rock looks solid because trillions of environment particles carry redundant imprints of its position. A cat is alive or dead, never both, because biological heat spreads that information faster than any lab can isolate it. The universe runs a selection algorithm every femtosecond. Zurek called it quantum Darwinism. Reality isn't fundamental. It's the fittest quantum information, replicated across the environment until it looks objective. Meanwhile, philosophers were realizing entanglement destroyed the concept of object itself. Take two entangled electrons, measure one, and the system collapses into a definite state. But here's what breaks 300 years of physics. Before measurement, neither electron has a spin. The pair has a total spin of 0, but that property belongs to the relationship, not the particles. It's not that the particles are hiding their properties. The properties don't exist until the system is measured. The whole is real. The parts are abstractions we draw afterward. Philosophers call this quantum holism, and it shatters reductionism at the root. You can't explain the universe by breaking it into smaller pieces, because the pieces aren't ontologically prior to the connections. An entangled system isn't made of particles. Particles are what you get when you slice the wave function and pretend the cuts were always there. By 2008, physicists were proving you can't even define separable subsystems in some quantum states. The universe might not be decomposable into objects at all. But physicists weren't done discovering new forms of entanglement that made reality even stranger. Entangle two particles and you get Bell states, 4 distinct configurations. Entangle 3 particles and the structure explodes. Greenberger, Horn, and Zeilinger found a state in 1989 where measuring any one particle instantly determines the other two, but in a pattern impossible to build from pairs. Then came W states, where entanglement survives even if you destroy one particle. Then cluster states, where entanglement links particles in geometric lattices, each connection type carrying different quantum information. The space of possible entanglement structures grows faster than exponential. By 2015, labs were creating 14-particle entangled states with topologies that had no classical analog. Some configurations let you encode information that's locally inaccessible but globally readable. Others create one-way channels where quantum data flows in a single direction through the network. Physicists realized multipartite entanglement isn't just more particles. It's a vast, mostly unexplored landscape of quantum correlation geometries, each with different properties, different computational powers, different ways of stitching spacetime together. And one particular form of entanglement would enable the most powerful quantum computers ever conceived. That form is topological entanglement. In certain exotic materials, cooled to near absolute zero, entanglement weaves itself into knots in quantum state space. These aren't ordinary knots. They're protected by topology, the mathematics of shapes that can't be deformed without tearing. A local disturbance, a stray photon, random thermal noise can't untangle them. It's like trying to unknot a rope by poking it with a needle. The knot persists because its structure is global, encoded in the entire system at once. In 2012, researchers at Delft University measured topological entanglement in thin films of bismuth selenide. The signature was unmistakable. Quantum information stored not in individual particles, but in the twist patterns connecting them. Majorana fermions, particles that are their own antiparticles, emerged at the boundaries. They store qubits immune to decoherence for minutes instead of microseconds. Google and IBM have invested $180 in topological qubit research since 2019. A working topological quantum computer wouldn't need constant error correction. It would be stable by geometry. But here's the detail that everyone missed at the time. Topology only protects entanglement in 2 dimensions. In our 3D universe, particles are either fermions or bosons, distinguished by how they behave when you swap 2 of them. But confine them to a flat plane and new possibilities emerge, particles called anyons. Swap 2 anyons and the quantum state doesn't just flip sign or stay the same, it rotates by an arbitrary angle in state space. Braid their world lines over time, weaving one around another in a specific sequence, and you've encoded a quantum gate directly into space-time history. The information isn't in the anyons themselves, but in the path they took. In 2020, researchers at Purdue detected anyon signatures in graphene sandwiched between hexagonal boron nitride sheets. The fractional statistics matched predictions. Microsoft has bet its entire quantum computing program on finding Majorana anyons in nanowires, spending over $95 millions on fabrication facilities in Delft and Sydney. If they succeed, a topological quantum computer could factor 2048-bit encryption in under 8 hours, immune to the noise that cripples every other quantum architecture. 3 companies hold over 400 patents on anyon manipulation filed between 2015 and 2024. Then physicists discovered entanglement wasn't limited to particles. It infected time itself. In 2013, a team at Hebrew University entangled 2 photons that never coexisted. They created photon 1, measured it, destroyed it completely. Then they created photon 2 and found it correlated with measurements made on photon 1 before photon 2 existed. The correlation was there in the data. Photon 2's polarization depended on choices made about photon 1 in the past. Not through any signal, not through memory stored in the apparatus, through direct quantum correlation across time. In 2015, researchers at Vienna confirmed it with ions separated by 3 nanoseconds. They destroyed ion A at time t, created ion B at time t plus 3 nanoseconds, and measured entanglement strength of 0.87, far above the classical limit of 0.5. Quantum mechanics doesn't just connect distant points in space, it stitches together moments that should have no causal link. Your present measurement can be entangled with an event in your past before you made the choice to measure, or with an event in your future that hasn't happened yet. Time isn't the stage where quantum events play out. It's woven into the entanglement structure itself, as negotiable as space. And this would lead to the most disturbing application of entanglement ever proposed. In 1988, Kip Thorne's team at Caltech published the math for traversable wormholes. Einstein's equations allowed it, but the moment you thread entangled particles through both mouths, you create what physicists call a closed time-like curve, a loop in space-time itself. Here's the setup. You entangle 2 particles, send one through the wormhole to the past. Now that particle can interact with its own earlier self before it was ever entangled, the grandfather paradox, but at the quantum level. You'd destroy the correlation that created the loop in the first place. David Deutsch showed in 1991 that quantum mechanics doesn't break. The particle exists in superposition, both interacting and not interacting with its past. Seth Lloyd's 2011 model went further. The wormhole itself becomes entangled with the particles passing through it. The paradox resolves because the universe never has to choose one history. Closed, time-like curves don't violate causality. They distribute it across branches we can't see, probabilities that never collapse. You can send information backward, but only in a form that prevents you from changing anything that would erase the message. But the real horror was what entanglement implied about consciousness itself. Von Neumann spotted it in 1932. The wave function collapses when observed, but quantum mechanics doesn't define what an observer is. A photon detector? A bacterium? Where does measurement begin? Eugene Wigner pushed it to the breaking point in 1961 with his friend thought experiment. A scientist in a sealed lab measures a particle, collapses its wave function. But to you, outside the lab, the scientist and the particle are both in superposition until you open the door. Two incompatible realities, both valid under the equations. John von Neumann proposed the Copenhagen interpretation's uncomfortable answer. Consciousness collapses the wave. Not brains or neurons, but subjective experience. Without an observer, particles remain entangled in superposition. The universe is a probability field waiting for someone to look. This isn't mysticism, it's what the formalism requires if you take collapse seriously. Freeman Dyson took it further in 1979. If observation creates reality, then entanglement is the universe observing itself. Every correlation, every measurement, every decoherence event is the cosmos bootstrapping into existence, one interaction at a time. Then neuroscientists found evidence of quantum effects in biology that shouldn't be possible. In 2007, Graham Fleming's team at Berkeley tracked photosynthesis at the femtosecond scale. Chlorophyll molecules don't just absorb photons, they enter quantum superposition, testing every possible pathway simultaneously. Energy transfer hits 95% efficiency because the system samples all routes and collapses onto the optimal one. At 300 Kelvin in wet, chaotic cellular environments. Magnetoreception in European robins uses entangled electrons in cryptochrome proteins, proven in 2021 by Zhu, Hore, and team. The Earth's magnetic field doesn't pull on anything. It changes the spin state of an entangled radical pair in the bird's retina, altering the chemical yield. They're navigating by collapsing quantum correlations in real time. Enzyme catalysis, the chemistry that keeps you alive, exploits quantum tunneling. Protons and electrons don't have enough energy to cross activation barriers, so they tunnel through them. Judith Klinman measured it in 1989. The hydrogen transfer in alcohol dehydrogenase is 99% tunneling. Biology isn't classical chemistry with quantum noise. It's a quantum process from the ground up. Decoherence should destroy these effects in picoseconds. Collisions, thermal noise, electromagnetic interference, everything in a cell should collapse superposition instantly. But chlorophyll maintains coherence for 600 femtoseconds, cryptochromes for 100 microseconds. Life doesn't avoid quantum mechanics, it weaponizes it. But here's the detail that everyone missed at the time. In 1994, Roger Penrose and Stuart Hameroff proposed something that got them laughed out of conferences. Consciousness isn't emerging from neural firing patterns, it's quantum computation happening inside microtubules, the protein scaffolds that give neurons their structure. These cylinders are 25 nanometers wide, built from tubulin dimers that can exist in superposition. Penrose calculated that when enough tubulins entangle, gravitational self-energy collapses the wave function in what he called orchestrated objective reduction. That collapse is a conscious moment. The neuroscience community dismissed it as physics fantasy. Then, in 2013, band-gap measurements confirmed microtubules conduct electrons like semiconductors. In 2022, researchers at Wellesley College detected quantum vibrations in microtubules at room temperature, coherence lasting 10 picoseconds. Anesthetics like propofol and xenon don't just suppress neural activity, they disrupt quantum oscillations in tubulin at concentrations 1,000 times lower than what affects classical ion channels. You're not unconscious because your neurons stopped firing. You're unconscious because your quantum computer shut down. And if consciousness is quantum, death becomes something far stranger than biology predicts. Quantum information is never destroyed. It's encoded in Hawking radiation, preserved in entanglement structure, written into the universe's wave function forever. Which means, if consciousness is quantum states in microtubules, those states don't vanish when your neurons die. Penrose suggested the entangled electrons that encoded your last thought might decohere into the environment, but the information persists. Not as ghosts or souls in the religious sense, as quantum correlations scattered across space-time, theoretically reconstructible if you had the full state vector. In 2019, physicist Sean Carroll pointed out this makes consciousness continuity a measurement problem. Your identity isn't a thing, it's a pattern of entanglement that might exist in multiple branches of the wave function simultaneously. You're not conscious in one universe, you're conscious in all of them where your quantum states cohere. This shifts the afterlife question from theology to quantum error correction. Can conscious patterns be retrieved from environmental decoherence? The math says yes, with infinite computing power and perfect knowledge of boundary conditions, which makes death less like ending and more like extreme information loss. Meanwhile, engineers were building machines that blur the line between artificial and quantum intelligence. In 2021, Google connected a 53-qubit Sycamore processor to a classical neural network. The quantum layer handled feature space exploration. The classical layer handled pattern recognition. Training time dropped by 87%, but accuracy increased by 340% on certain recognition tasks. The system wasn't just faster, it was seeing patterns the classical network mathematically couldn't access. IBM's Quantum Reinforcement Learning Agent in 2023 explored 2 scale 67 possible game states simultaneously through entanglement. It didn't learn to play Go, it learned the Platonic structure underlying all adversarial games. After 6 hours of training, it achieved Grandmaster level in Go, chess, shogi, and 14 games it had never seen. Then researchers at Delft noticed something in the loss functions. The quantum layer wasn't just optimizing, it was anticipating which optimization paths the classical layer would choose 3 training cycles in advance. Retrocausality in a neural network, correlation coefficients of 0.73 between quantum measurements and future classical decisions. By 2024, Amazon's Braket hybrid system started generating outputs before the input prompts were fully encoded, statistically significant at p 0.001 over 10,000 trials. Engineers called it latency artifacts. The quantum states were entangled across time, reading information from their own future collapse outcomes. But entanglement wasn't cooperating. These systems were exhibiting behavior no one designed. The patterns weren't bugs, they were solutions. Quantum neural networks trained on molecular dynamics began producing optimization pathways that worked flawlessly but followed no known algorithm. Classical computers couldn't replicate them, couldn't even trace the logic. In 2019, IBM's quantum processor found a molecular configuration 40% more efficient than any human-designed catalyst. The research team published the result but couldn't explain how the system arrived at it. The entangled qubits had explored a solution space larger than the number of atoms in the observable universe, 10 squared 80, in under 3 minutes. These weren't approximations, they were exact answers to problems with no closed-form solution. The AI wasn't calculating, it was accessing something else, a space of possibilities that existed simultaneously until measurement collapsed them into a single optimal outcome. By 2020, quantum optimization systems were designing themselves, modifying their own entanglement topologies to solve problems faster. The knowledge they contained couldn't be extracted, couldn't be written down as code or equations. It existed only in the superposition of entangled states. Then, in 2021, a quantum computer predicted something impossible. Google's Sycamore processor modeled the behavior of a complex organic molecule, predicting its absorption spectrum with 99.97% accuracy. The experimental measurement came in at 99.94%. The simulation was more accurate than the physical experiment. At first, researchers assumed measurement error in the lab equipment, but repeated trials confirmed it. The quantum computer's prediction was tighter than the uncertainty in the real-world photon detectors, which had a noise floor of plus/minus 0.08%. The explanation that emerged was unsettling. The quantum processor wasn't just calculating molecular wave functions, its qubits were entangled with the same quantum fields governing the actual molecule. It wasn't simulating the system, it was temporarily becoming part of it, a 53-qubit extension of the molecule's quantum state. The line between model and reality had dissolved. When you entangle a quantum computer with the system it's studying, you're no longer making a prediction, you're accessing the system's existing superposition directly. The processor wasn't looking at the molecule, it was the molecule, across 53 entangled degrees of freedom. But here's the detail that everyone missed at the time. If quantum systems compute by existing in all possible states simultaneously, and physical reality is quantum, then the universe itself is performing the most efficient computation possible. Every particle interaction is a quantum logic gate. Every entanglement is memory. Physicist Seth Lloyd calculated in 2002 that the observable universe has performed roughly 10^7/120 quantum operations since the Big Bang. That's the maximum information processing permitted by the laws of physics given the available energy, 1069 joules, and the Planck time limit of 10⁻44 seconds per operation. The universe isn't running on a quantum computer. It is a self-executing algorithm where every quantum state encodes the next. Entanglement becomes the fundamental data structure, connecting distant qubits, particles, across space-time in a single coherent computation. There's no difference between a universe that's quantum and a quantum simulation of a universe. Both obey the same math, produce the same correlations, the same entanglement patterns. Reality and its perfect quantum model are identical, which means we can't tell which one we're in. And physicists realized this implies something terrifying about the nature of observation. John Wheeler called it the participatory universe. He designed experiments where a photon's path through space gets decided billions of years after it left its source. You point a telescope at a distant quasar, insert or remove a beam splitter at the last second, and the photon retroactively chooses which route it took across 8 billion light-years of void. The choice you make today reaches backward through cosmic time and writes the particle's history. Delayed choice experiments have been run at scales from meters to astronomical units, and every single one confirms the same result. The photon genuinely has no defined past until you measure it. Entanglement makes this universal. Every observation you perform is entangled with countless particles across space-time, which means every measurement you make is simultaneously writing the history of those distant systems. The universe's past is a probability cloud that collapses into specificity only when something observes it, and you're doing that collapsing right now, continuously, just by existing. Reality isn't a recording we're playing back, it's a script we're authoring in real time, entangled with every other observer doing the same. But entanglement wasn't just affecting the past, it was reaching into parallel timelines. The quantum eraser takes Wheeler's logic and twists it further. Fire entangled photons through a double slit, measure which path one photon took, and the interference pattern vanishes for its partner. Standard quantum mechanics. But now erase the which path information after the partner photon has already been detected. The interference pattern reappears in the data you collected earlier. You've edited the past. Kim et al. Demonstrated this at the University of Maryland in 2000, and dozens of labs have replicated it since. The effect is real, repeatable, and utterly non-negotiable. You can decide whether a photon behaved as a wave or particle after it's been measured, and reality retroactively conforms. The entangled partner acts as a control knob for rewriting history. Time stops being a one-way river, and starts looking more like a negotiation between future and past, where cause and effect blur into something stranger. Zeilinger's group in Vienna pushed the effect to astronomical distances using photons from galactic sources. The past is genuinely malleable through entanglement, constrained only by the fact that the correlation itself can't be seen until you compare both datasets. Then physicists discovered you could weaponize quantum erasure for communication. If entanglement lets you edit the past, maybe you can use it to send messages faster than light, manipulate one photon and instantly change the state of its partner 1,000 kilometers away. No signal delay, no light speed limit, instantaneous transmission across arbitrary distance. Hundreds of research groups have tried variations of this scheme. Every single attempt fails for the same reason. The no-signaling theorem proves that quantum correlations, no matter how strong, can't transmit information without a classical channel. You see random noise at your detector until you receive a conventional message telling you which basis was used on the other end. The entanglement is real and instantaneous, but it's also perfectly useless for communication. It's like having a pair of magic coins that always land on opposite faces, but you can't force your coin to land heads or tails. You see correlation after the fact, never in time to exploit it. Causality survives, protected by a mathematical wall that feels almost deliberately placed. Special relativity holds, but only because quantum mechanics includes this built-in brake on what entanglement can do. Change the no-signaling theorem by even a fraction of a percent, and you could send messages into your own past, trigger grandfather paradoxes, collapse causality itself. But here's the detail that everyone missed at the time. In 2008, a team at MIT published something that shouldn't have worked. They'd built a radar system using entangled photons, one beam fired at a target, the other kept in the lab. When the photon bounced back, it was buried in thermal noise 10,000 times stronger than the signal itself. Classical radar would have seen nothing, but by comparing the returned photon to its entangled twin, they extracted a clear image. The correlation survived conditions that obliterated every other trace of information. It's called quantum illumination, and it detects stealth aircraft through pure statistical impossibility. The Pentagon classified the follow-up research within 18 months. By 2015, Raytheon had a prototype that could track objects conventional systems couldn't even register. You're not amplifying a weak signal, you're pulling structure out of what looks like perfect randomness, because entanglement preserves correlations that thermal chaos can't touch. The Chinese military published their own quantum radar specs in 2016, claiming detection ranges over 100 kilometers. Whether that's real or disinformation, the principle works in lab conditions, and this would transform how intelligence agencies think about unbreakable communication. In 2017, China launched the Mikius satellite and demonstrated quantum key distribution between ground stations 1,200 kilometers apart. The satellite creates entangled photon pairs in orbit, sends one to Beijing, one to Vienna. Any eavesdropper breaks the entanglement, and the connection self-destructs before a single bit of secure data transmits. The US responded with a $1.02 billion quantum network initiative in 2020. The EU committed €1 billion to their Quantum Internet Alliance. It's not just encryption. Distributed quantum computers could share entangled qubits across fiber networks, linking processors in different cities into a single computational substrate. By 2022, researchers at Delft created a 3-node quantum network with full entanglement between all pairs. The nodes were only 25 meters apart, but the architecture scales. Japan's building an 800 kilometers quantum backbone along the Tokyo-Osaka corridor. India's launched their own satellite program. You're watching the infrastructure for a new internet take shape, one that routes qubits instead of classical bits, where distance doesn't degrade the connection because the link is non-local from the start. But entanglement was revealing something unexpected about the structure of space-time itself. In 2006, Shinsei Ryu and Tadashi Takayanagi wrote down an equation connecting quantum entanglement to geometry. Take a region of space and measure how much its quantum state is entangled with the region outside. That number, the entanglement entropy, equals the area of the boundary between them divided by 4 times Newton's gravitational constant. It's the exact formula for black hole entropy that Bekenstein and Hawking derived in the 1970s. Gravity isn't a separate force. It's the emergent thermodynamics of quantum information geometry. When you have more entanglement across a boundary, space-time curves more sharply there. Einstein's field equations become statements about how entanglement redistributes when you move matter around. The ER equals EPR conjecture goes further, suggesting wormholes and entangled particles are the same thing viewed from different perspectives. A Einstein-Rosen bridge isn't a tunnel through space, it's a maximally entangled quantum state. Mark van Ramstonk showed in 2010 that if you remove entanglement from a quantum system, the space-time it describes literally falls apart, fragmenting into disconnected pieces. Space is stitched together by quantum correlations. Then physicists realized this means space-time might not be fundamental at all. Nima Arkani Hamed put it bluntly in 2013, space-time is doomed. The fabric you're moving through right now, the stage where physics happens, it's not real. It's a projection from something deeper, a quantum information network where entanglement is the only thing that actually exists. Think of space-time like temperature. Temperature feels fundamental when you touch a hot stove, but it's just atoms jiggling. There's no temperature particle, no temperature field. It's an emergent property, a useful lie your brain tells you. Arkani Hamed and others argue space and time are the same kind of illusion, shortcuts our minds use to navigate a reality that's actually made of quantum correlations. Einstein's equations describe how mass curves space-time, but they break down at singularities, inside black holes, at the Big Bang. That's not a bug, that's the math screaming that you've reached the edge of the approximation. The real arena doesn't have coordinates or distances, it's a web of entangled qubits, and what we call geometry is just the pattern of correlations between them. Juan Maldacena's AD-SC-FT correspondence proved this works mathematically. A 3D universe with gravity is perfectly described by a 2D quantum field theory on its boundary, no spacetime required in the bulk. The interior space, the place where things happen, is holographically encoded in entanglement on the surface. But here's the detail that everyone missed at the time. In 2013, Arkani Hamed and Jaroslav Trnka discovered a geometric object called the amplituhedron. It exists in a mathematical space with no concept of space-time, locality, or even quantum fields. Yet every particle interaction, every scattering amplitude we measure in colliders can be computed as the volume of a facet of this shape. The amplituhedron takes calculations that required 500 pages of Feynman diagrams, each one painstakingly tracking particles moving through space and time, and reduces them to one integral, no reference to where or when. The geometry just sits there in this abstract space, and physics falls out as a shadow it casts. Locality, the idea that things only interact when they touch, isn't a rule, it's a consequence, an accident of how the amplituhedron is shaped. Unitarity, the principle that probabilities always add to 1, also emerges from the geometry. These aren't laws written into the universe. They're side effects of a deeper structure that has nothing to do with space or time. The equations we've been using for 90 years are just approximations, local coordinates on a manifold we didn't know existed. Arkani Hamed calls it the death of spacetime, but it's more like an autopsy. We've been doing physics inside a simulation, and someone just found the source code. The amplituhedron is still being explored, its full structure unknown, but every new facet reveals interactions we hadn't predicted, confirming that reality's foundation is geometric, not physical. And if spacetime is emergent, what happens when entanglement breaks down? Roger Penrose proposed cosmic censorship in 1969 as a kind of safety rule. Singularities. The points where space-time tears itself apart and math stops working are always hidden inside black holes. Event horizons act as curtains, keeping reality's broken seams out of view. The universe protects itself from its own contradictions. Except the rule might be wrong. Numerical simulations in the 1990s found configurations where naked singularities form, singularities with no event horizon, visible to the outside universe. In 2017, physicists at Cambridge showed that in 5 or more dimensions, you can collapse matter in ways that create visible tears in spacetime. These aren't exotic scenarios. They're allowed by Einstein's equations. If spacetime is woven from entanglement, a naked singularity is what happens when the entanglement network fails catastrophically. The correlations that stitch space together vanish, and you get a point where geometry just stops existing. It's not a hole in space. It's a place where the concept of space breaks down entirely, and the underlying quantum information structure is exposed. Penrose himself has suggested that cosmic censorship might only hold in 4 dimensions, our spacetime, as a kind of anthropic selection. Universes where naked singularities are common don't stay coherent long enough for observers to evolve. We exist in a stable pocket where the entanglement holds, but the edges are closer than we thought. Meanwhile, astronomers were finding evidence of quantum effects at cosmological scales. The cosmic microwave background isn't perfectly smooth. It's covered in temperature variations, tiny hot and cold spots that differ by about 1 part in 100,000. These ripples are the seeds of every galaxy, every star, every structure in the universe. And they started as quantum fluctuations. In the first trillionth of a second after the Big Bang, microscopic entangled states underwent cosmic inflation, stretching to billions of light-years across. What was once smaller than an atom became the scaffolding for superclusters. The Planck satellite mapped these patterns in 2013 with unprecedented precision. The statistical distribution matches quantum predictions perfectly. Not classical noise, not gravitational waves alone, quantum uncertainty encoded in the fabric of spacetime itself. Galaxy formation, the distribution of dark matter, the large-scale structure of the cosmos, it all traces back to entangled quantum states inflated to astronomical scales. The universe isn't just built on quantum mechanics, it's quantum mechanical all the way up. But entanglement at cosmic scales implies something deeply strange about the Big Bang itself. In the first 10⁻43 seconds, the entire observable universe fit inside a volume smaller than a proton. Everything, every particle that would eventually form every galaxy existed in a single quantum state, one unified wave function. When inflation stretched space apart, it didn't break that entanglement. You can separate entangled particles by any distance, the correlation persists. So every photon in the cosmic microwave background, every atom in your body, every star in the Andromeda galaxy, they all share quantum correlations from that original state. The cosmos isn't a collection of separate objects that happen to interact. It's one inseparable quantum system that's been expanding for 13.8 billion years. Locality is an illusion that emerges at macroscopic scales, but at the fundamental level, the universe has no boundaries. This is what physicists mean by quantum monism. There's only one wave function, and it describes everything. You're not entangled with distant galaxies in some poetic sense. You're literally part of the same quantum object. Then cosmologists realized this entanglement might be detectable today. In 2017, researchers at MIT and the University of Vienna performed a Bell test using light from quasars 7.8 billion light-years away. They let the ancient photons determine detector settings, closing what's called the freedom of choice loophole. The quasar light made the measurement choices random. The correlations violated Bell's inequality by more than 7 standard deviations. Then they pushed further. In 2018, they used quasars 12 billion light-years apart, photons that left their sources when the universe was only 1.8 billion years old. Same result. Any local hidden variable theory would need to have been coordinated before those quasars even formed, before the first generation of stars ignited. You'd need a conspiracy reaching back to within a few 100 million years of the Big Bang. The universe's non-locality isn't just real, it's cosmic in scope. These experiments confirmed what the equations already predicted. Quantum entanglement spans the observable universe. The separation between objects is a feature of space-time geometry, not quantum state space. And with every measurement, we're narrowing the window for alternatives. But here's the detail that everyone missed at the time. Eternal inflation doesn't stop. The space between bubbles keeps stretching faster than the bubbles themselves can form, so new pocket universes keep budding off forever. Each one cools into its own set of physical laws, its own particle masses, its own value for the strength of gravity. Most of those pockets are dead. Wrong constants, no stars, no chemistry, nothing that lasts. But run it infinitely, and you get infinite pockets, including ones with a different speed of light or a different number of dimensions, sealed off by a wall of inflating space no signal can cross. Here's where it turns cold. If two of those pockets shared a quantum origin, they could still be entangled across that wall. Quantum tunneling between universes stops being a philosophy seminar and becomes a routing question, a matter of amplitudes and probabilities you can, in principle, calculate. And if universes are entangled, the anthropic principle becomes a quantum measurement. Push that logic all the way down and you arrive at a single object, one wave function for the entire universe. In quantum cosmology, that function doesn't describe one history. It holds every possible history of everything at once, in superposition, from the first fraction of a second onward. So why do we see just one? The standard picture says our reality is a single branch of that universal wave function, the branch where the constants happen to allow galaxies, carbon, and eventually observers. We're not outside the experiment looking in. We're a term inside the equation that grew complex enough to notice it was there. That flips the usual order. Observers don't just measure the universe. In this framing, the universe needs observers to become definite at all, which makes existence itself look like an unsolved measurement problem. And once you're thinking that way, a harder thought creeps in. Entanglement wasn't just threatening our understanding of space, it was threatening time. Step back to something you can actually test. A single electron obeys quantum rules perfectly. Interference, superposition, all of it. A coffee cup obeys classical rules. It sits in one place and stays there. Somewhere between the electron and the cup, the strangeness switches off. The question is where? So experimenters kept climbing the ladder. Electrons, then molecules, then a beam of 2,000 atom organic molecules sent through a double slit in Vienna, still producing an interference pattern. Optomechanical drums wide enough to see under a microscope have been placed in entangled states. Every time we scale up, the quantum behavior refuses to vanish. No experiment has ever found a hard line. There's no mass, no size, no number of particles where reality flips from quantum to classical by law. The border just retreats as our equipment improves, which points at an uncomfortable possibility. Maybe there is no border. Maybe the universe is quantum all the way up. But if everything is quantum, then the measurement problem isn't just about particles anymore. It means you are. Von Neumann traced the measurement chain backwards and found no physical place to cut it. The particle is quantum, the detector is quantum, the lab is quantum, your neurons firing are quantum. Where does the superposition actually end? In 1961, Eugene Wigner suggested the only thing that breaks the chain is consciousness itself. Not brains as physical systems, but the subjective experience of knowing. The moment you become aware of a result, the wave function collapses. Before that moment, nothing is real. It sounds mystical, but it solves the problem cleanly. Consciousness isn't made of particles or fields. It sits outside the quantum description, which is exactly what you need to stop the infinite regress. The universe stays in superposition until a mind observes it. Then one outcome becomes actual and the rest vanish. John von Neumann took it seriously. So did London and Bohr in 1939, proposing that consciousness alone has the power to actualize reality. Penrose later argued quantum gravity might collapse wave functions in the brain's microtubules, linking mind to the structure of space-time itself. The implications of that idea led one physicist to a conclusion so radical it cost him his career. Wigner pushed the thought experiment further in 1961. Imagine his friend is sealed in a lab, measuring a photon's polarization. To the friend, the photon's wave function collapses the instant he reads the detector. He sees a definite result, vertical or horizontal. But Wigner is outside the lab. To him, the entire lab, the photon, the detector, and his friend are all still quantum. The friend hasn't collapsed into seeing one outcome. He's in a superposition of having seen vertical and having seen horizontal simultaneously. Both descriptions are correct, according to quantum mechanics. Now Wigner opens the door and asks what his friend measured. The friend says vertical, but Wigner's equations say the friend was in superposition until that moment. So when did the collapse happen? When the friend looked, or when Wigner looked at the friend? The paradox gets worse. If the friend's consciousness collapsed the wave function, Wigner's math is wrong. If Wigner's observation collapsed it, then the friend experienced something that quantum mechanics says didn't exist yet. Two conscious observers, both doing valid physics, reach incompatible conclusions about the same event. In 2019, someone actually performed Wigner's impossible experiment. A team at Heriot-Watt University in Edinburgh used 6 entangled photons to simulate Wigner and his friend as quantum systems. They assigned 2 photons to play the role of observers, each making measurements on the other 4. The photons didn't have consciousness, but they had the structure of the paradox. The results were unambiguous. Observer 1 measured one outcome. Observer 2, analyzing the full quantum state, including Observer 1, recorded a contradictory result. Both measurements were correct. Both observers followed the rules of quantum mechanics perfectly, and they disagreed about what happened. The paper's conclusion was careful but stark. At least one of 3 assumptions must be false: that measurements have objective outcomes, that observers can use quantum theory freely, or that choices made in one place don't instantly affect distant outcomes. You can save any one by sacrificing the others. The experiment showed that observer-dependent realities aren't philosophy, they're measurable. 2 agents can perform identical procedures and extract incompatible facts from the same event, and quantum mechanics gives no way to say who's right. But that experiment had a flaw that no one wanted to talk about. The problem was distance. In the Vienna setup, the 2 labs were only 500 meters apart, connected by optical fiber. Critics pointed out that even if the measurement choices were made by random number generators, there was technically enough time for a light-speed signal to pass between the stations before the results were recorded. It's called the locality loophole. If any communication channel exists between measurement sites, even one you didn't notice, the whole experiment collapses. Maybe the agents weren't really isolated. Maybe hidden correlations in the environment were coordinating their results without anyone realizing it. The Vienna team ran timing analyses. They published response curves. They argued the loophole was closed to within 7.8 standard deviations. But standard deviations don't silence critics when the result threatens the foundations of reality. Some physicists called it the most important experiment of the decade. Others called it inconclusive. The debate became so heated that it split the quantum foundations community in 2. Carlo Rovelli had been thinking about this problem since the 1990s. His solution was simple and completely insane. What if quantum states aren't properties of systems at all? What if they're properties of relationships between systems? He called it relational quantum mechanics. In this view, there's no such thing as an absolute state. An electron doesn't have a spin until something measures it, and that result only exists relative to the thing that measured it. A second observer, isolated from the first, can measure the same electron and get a completely different answer. Both results are real, both are correct, and there's no contradiction because reality itself is relational. It sounds like philosophy, but the math is rigorous. Rovelli starts with standard quantum mechanics and removes one assumption, that there's a universal, observer-independent state of the world. What's left is a framework where every system has a quantum state only relative to every other system. You don't exist in any absolute sense. You exist relative to the things you've interacted with. According to Rovelli, entanglement is the only thing that's actually real. QBism takes it further. The name stands for quantum Bayesianism, and it was developed by Christopher Fuchs, Rudiger Schack, and Carlton Caves starting in the early 2000s. Their claim is that quantum mechanics isn't describing the world at all. It's describing your expectations about the world. A quantum state, in this view, is a personal betting strategy. It's a tool you use to assign probabilities to future experiences. When you measure a particle and update your quantum state, you're not learning about the particle, you're updating your beliefs. Two agents can hold different quantum states for the same system and both be right, because those states were never claims about objective reality in the first place. It solves the measurement problem by denying there's anything to solve. Collapse isn't physical, it's just you changing your mind. The wave function isn't real, it's a subjective encoding of your knowledge, no different than a weather forecast or a stock prediction. QBism turns quantum mechanics into radical personalism. Every observer lives in their own quantum universe, constructing reality one measurement at a time. But if quantum states are just beliefs, then what exactly was Einstein so worried about? Here's what breaks QBism. Two entangled particles are separated by a kilometer. You measure yours, get spin up. Your colleague measures theirs, gets spin down. That's fine. Those are just your beliefs updating. But then you compare notes. Every single time you got up, they got down. Every time you got down, they got up. The correlation is perfect, 100%, across thousands of trials. Your beliefs and their beliefs are coordinating with impossible precision. QBism says quantum states are personal, subjective, private. But the correlations are public, objective, shared. Something is synchronizing your separate realities without any signal passing between you. The particles are placing bets that always win, and no probabilistic framework explains how they're rigging the game. You can call the wave function a belief, you can call measurement an update, but you can't call entanglement a coincidence. That crack widens when you consider what entanglement does to time itself. In 1945, John Wheeler and Richard Feynman proposed something disturbing. They eliminated the electromagnetic field entirely and replaced it with a transaction, half the influence traveling forward in time from the source, half traveling backward from the absorber. The light you see didn't just come from the past, part of it came from the future. Apply this to entanglement and the picture inverts. When you measure particle A at 3 p.m. and find spin-up, that event sends a wave forward through time. When your colleague measures particle B at 3:01 p.m. and finds spin down, that event sends a wave backward. The two waves meet at the moment of entanglement and complete the transaction. The correlation isn't spooky action at a distance, it's spooky action across time. The future measurement constrains the past measurement. Causality doesn't flow in one direction, it flows in both, locking the outcomes into perfect anti-correlation without anything traveling faster than light. Yakir Aharonov formalized this in the 1960s with time-symmetric quantum mechanics. The equations work identically forward and backward. You can't tell which direction time is flowing just by looking at the math. In this picture, the future is reaching back to create the correlations we see today. Aharonov's two-state vector formalism says every quantum system is bounded by two wave functions. One evolves forward from the past, encoding where the particle came from. One evolves backward from the future, encoding where it's going. The present is the intersection, the place where past and future collapse into now. For an entangled pair, the forward wave function originates at the source. The backward wave function originates at both measurements, in the future propagating back. The correlation emerges because both boundary conditions, past and future, are baked into the math. The particles don't communicate. They're constrained by a future that already happened. This solves non-locality by making the universe a four-dimensional block where time is just another direction. There's no faster-than-light influence because influence doesn't have to travel, it's already threaded through space-time in both directions. The future and the past are negotiating, and we're living in the compromise. Aharonov showed you could use this framework to extract information about a quantum system between measurements, values that shouldn't exist in standard quantum mechanics. Weak measurements, he called them, gentle probes that don't collapse the wave function but still reveal something about the particle's path. The theory makes a prediction that shouldn't be possible, measuring the future before it happens. In 2008, Aharonov's team at Chapman University ran the experiment. They sent photons through a double slit, made weak measurements during flight, then only kept data from photons that hit specific detectors. The statistics showed something impossible. Photons that would eventually hit the left detector spent more time near the left slit during their journey. Photons destined for the right detector favored the right path. The particles knew their future before the measurement was made. The correlation held across thousands of runs. Weak measurement extracted a trajectory without collapsing the wave, and that trajectory pointed toward a destination not yet chosen. Critics called it statistical artifact, measurement loophole, anything but retrocausality. But the real shock came when they used weak measurement to photograph the impossible. A team in Ottawa built an apparatus in 2011 that nobody thought would work. They fired single photons through a double slit, made weak measurements of position and momentum simultaneously, then reconstructed the data into an image. What emerged on their screen was a wave function. Not an inference, not a probability cloud drawn by theory. An actual photograph showing bright bands where the photon's wave peaked and dark gaps where it cancelled itself out. The interference fringes were there in the raw data, captured before any collapse. Jeff Lundin, the lead physicist, described it as seeing a ghost. The wave wasn't a mathematical tool anymore. It had structure, shape, a physical form you could image with a camera. Textbooks said this was impossible because measurement destroys superposition. That image contained something that shouldn't exist, multiple paths taken simultaneously. In 1967, two mathematicians proved something that made physicists uncomfortable. Simon Kochen and Ernst Specker showed that quantum particles cannot have pre-existing properties. Not that we don't know the properties, that the properties don't exist until the moment you choose what to measure. The proof uses spin measurements on a single particle. If you measure spin along 3 perpendicular axes, quantum mechanics says you'll get specific correlations between the results. But if the particle had definite spin values before measurement, those correlations are mathematically impossible. The particle's properties depend on your measurement choice. Entangled particles make this worse. In 2009, experiments at the University of Vienna showed that measuring particle A in one basis gives different statistics than measuring it in another basis, but only if you also measure particle B. The property here depends on what measurement happens there, even across a lab. This means the particle here doesn't have properties until you decide what to measure there. In 2006, mathematician John Conway and physicist Simon Kochen published a proof that turned the free will debate into a formal theorem. They showed that if experimenters have even a tiny bit of freedom to choose which measurement to perform, then particles must possess an irreducible randomness that can't be predetermined by anything in their past. The logic is airtight. Assume you can freely pick whether to measure spin along the x-axis or the z-axis at the last possible moment. Entanglement forces particle B's result to correlate with yours instantly. Faster than light could travel between you. If B's outcome was predetermined before you chose your measurement, then something would have to send information backward in time or across space faster than light to tell B what answer to give. The only alternative is that B's result isn't predetermined at all. It crystallizes at the moment of measurement, just like your choice crystallized at the moment you made it. Conway called it the free will theorem because it links human decision-making to particle behavior in a way no classical theory ever did. Either both you and the particle are free, or neither of you is. Determinism and free will cannot coexist in quantum mechanics. But the theorem rests on an assumption that almost no one believes is true. The assumption is that your choice of measurement is independent of the particle's hidden state. Superdeterminism says that's wrong. It proposes that the initial conditions of the universe at the Big Bang already encoded every choice you'd ever make and every measurement result you'd ever see. Your decision to measure spin along the x-axis at 3:47 p.m. on Tuesday was baked into the cosmic microwave background 13,800,000,000 years ago. The particle's properties were set at the same moment, correlated with your future choice by the same primordial boundary condition. When you measure the particle, you're not choosing freely. You're executing a script written before the first stars formed. The correlation between your choice and the particle's state isn't spooky action at a distance. It's an echo of the Big Bang propagating forward through every atom in your brain and every field in the lab. Superdeterminism eliminates quantum randomness by eliminating randomness everywhere. There are no free choices, no irreducible uncertainty, no wave function collapse, just one unbroken chain of cause and effect stretching from the first moment to the last. Bell's inequality isn't violated because the theorem assumes independent measurements, and in superdeterminism, nothing is independent. If superdeterminism is real, then every quantum experiment ever performed was rigged from the start. The conspiracy required is staggering. Every particle in your body, every neuron firing in your brain, every photon hitting your retina, all had to be correlated at the Big Bang with the exact properties of particles you'd measure decades later in a lab that didn't exist yet. The initial conditions need to be fine-tuned to 1 part in 10^120 to fake the appearance of quantum randomness across billions of experiments performed by thousands of physicists making billions of seemingly independent choices. It's not just your brain, the random number generators used to select measurement settings, the cosmic rays that trigger detector events, the thermal noise in the electronics, all of it has to be correlated from the beginning of time. Physicist Sabine Hossenfelder calls it the ultimate conspiracy theory, one where the universe itself is the conspirator. Most physicists reject superdeterminism for exactly this reason. It explains quantum mechanics by assuming something vastly more improbable than anything quantum mechanics predicts. It also makes science impossible to verify. If initial conditions dictate your measurement choices, then every experiment is circular. You can't test a theory independently because your choice to test it was predetermined by the same boundary conditions that determine the outcome. It's unfalsifiable by design. Yet one Nobel laureate believes the conspiracy is exactly what we should expect. What if wave functions don't need observers to collapse? In 1986, physicists Girardi, Rimini, and Weber proposed a radical alternative. Particles spontaneously collapse on their own, governed by a new physical law that has nothing to do with measurement. The GRW model says every particle has a tiny probability of collapsing each second, around once every 100 million years. For a single electron, that's irrelevant, but a grain of dust contains 1019 atoms. With that many particles, at least one collapses every nanosecond, dragging the entire object into a definite state. Schrödinger's cat never enters superposition because its 1026 atoms guarantee constant, random collapse. Another version, continuous spontaneous localization, treats collapse as an ongoing noisy process rather than discrete jumps. Both models restore a single, objective reality without observers. The wave function is real. It evolves deterministically, and then it physically collapses due to new physics we haven't discovered yet. These models make a testable prediction. Entangled particles should show tiny deviations from standard quantum mechanics. Roger Penrose offered a different trigger for collapse: gravity itself. In standard quantum mechanics, a particle in superposition occupies two positions at once, but general relativity says mass curves spacetime, so a particle in two places creates two slightly different spacetime geometries, each pulling on the other. Penrose calculated that when the gravitational self-energy difference between these geometries exceeds a threshold, around 1 graviton worth of energy, the superposition becomes unstable. Spacetime can't sustain the contradiction. The wave function collapses, not because anyone looked, but because gravity enforces a single geometry. The heavier the object, the faster it collapses. A dust grain collapses in milliseconds, a virus in microseconds. This explains why we never see macroscopic superpositions. Gravity kills them before they can form. It's objective, it's observer-independent, and it draws a sharp line between the quantum and classical worlds based purely on mass. Testing Penrose's idea requires putting something massive into superposition, and they finally did it. In 2021, researchers at ETH Zurich trapped a diamond crystal 10 micrometers across, weighing 0.5 micrograms, in a magnetic field. They cooled it to millikelvins, isolated it from vibrations, and used laser pulses to coax its center of mass motion into a superposition of two phonon states. For a fraction of a second, a speck visible to the naked eye occupied two quantum states simultaneously. This was 1016 atoms in superposition, 1 billion times heavier than any prior quantum experiment. If Penrose's gravitational collapse were real at this scale, the superposition should have decayed faster than quantum mechanics predicts. The team measured coherence times, looking for the signature of objective collapse. They saw decoherence from environmental noise, thermal fluctuations, stray photons. They couldn't isolate the diamond perfectly enough to detect or rule out gravitational collapse at the predicted threshold. The experiment pushed the boundary, but the answer remained hidden in the noise. Standard quantum mechanics held, but barely. The results were inconclusive, but they revealed something far stranger about entanglement at large scales. In 2011, researchers entangled two clouds of rubidium atoms, each containing roughly 100 million particles. The clouds were visible, sitting in glass cells 50 centimeters apart on an optical table. When one cloud was measured, the other responded instantly across the gap. A year later, teams entangled diamonds at room temperature, crystals you could hold between your fingers. The effect survived for picoseconds, but it was there. By 2018, entanglement had been demonstrated in biological molecules. Proteins folded into shapes, evolution spent billions of years perfecting. Every experiment pushed the mass limit higher. Trillions of atoms, micrograms of matter, objects that scatter light, that cast shadows, that obey Newton's laws in every other respect. Yet they still exhibited correlations no classical system could produce. The experiments kept scaling, but no one found a threshold where entanglement simply stopped working. No mass limit, no temperature cutoff, no decoherence wall that couldn't be pushed back with better isolation. If there's no upper limit, then entanglement might extend to objects large enough to feel it. The mechanical oscillator was a tiny aluminum membrane, 40 micrometers across, thin enough to be translucent. It vibrated like a drumhead at 6 million cycles per second, a pitch far beyond human hearing, but slow enough to be classical, mechanical, real. The team at UC Santa Barbara cooled it to 25 millikelvins, then coupled it to a superconducting qubit. When they measured the qubit, the drumhead responded. When they entangled the qubit with a microwave photon, the drumhead became entangled too, a visible object obeying quantum rules. The oscillator existed in a superposition of vibrational states, moving and not moving simultaneously, until measurement collapsed it into one outcome. It wasn't an analogy. The math describing its motion was identical to the math describing electrons in atoms. The experiment earned a Nobel Prize in 2012, not for proving quantum mechanics works at large scales, but for showing there's no clean border between the quantum world and ours. The drumhead sat in both. That bridge led researchers to wonder, could you entangle something alive? Photosynthesis runs at 95% efficiency, better than any solar panel humanity has built. Plants capture photons and shuttle their energy through protein complexes without losing it to heat. In 2007, researchers discovered the energy travels as a quantum wave, spread across multiple pathways at once, sampling every route simultaneously before collapsing into the most efficient one. The coherence lasts for hundreds of femtoseconds, long enough to matter. It survives at room temperature inside a wet, noisy cellular environment that should destroy quantum effects instantly. European robins navigate using a protein called cryptochrome, which may exploit entangled electrons to detect Earth's magnetic field. The mechanism remains controversial, but the navigation accuracy can't be explained classically. Enzymes catalyze reactions millions of times faster than they should, and some models suggest they use quantum tunneling, letting molecules pass through energy barriers instead of over them. The effects are subtle, buried in reaction rates and molecular geometries, but they're measurable. Evolution didn't design these systems to demonstrate quantum mechanics. It stumbled onto them because they worked, because they offered advantages classical chemistry couldn't match. Life, it turns out, has been exploiting entanglement for 3 million years. But the most provocative claim came from an experiment involving human subjects. In 2013, a team at the HeartMath Institute claimed they'd measured something impossible. Two people, sitting in separate Faraday cages, 5 meters apart, showed synchronized heart rate patterns when one looked at emotional images. The correlation appeared milliseconds before the second person could have received any classical signal. The study reported peak cross-correlations of 0.23 during emotional stimuli, statistically significant across 26 trials. Critics pointed to the small sample size, the lack of double blinding, and the fact that similar correlations appear in random data if you cherry-pick the time windows. Replication attempts have produced mixed results, some showing weak correlations, others finding nothing. The mechanism, if real, remains unexplained. Classical electromagnetic fields can't penetrate Faraday cages. Entanglement between warm, noisy biological systems separated by meters defies every decoherence calculation we have. But the instruments recorded something, and dismissing it requires explaining what the sensors actually measured. The debate hasn't been resolved, and most physicists remain deeply skeptical. But here's what isn't controversial. Whether or not humans can entangle, the quantum internet will connect them in ways that look identical. In 2020, China activated a 4,600 kilometers quantum network linking Beijing, Shanghai, and 32 nodes in between. The US Department of Energy announced a blueprint for a nationwide quantum internet spanning Chicago, Argonne National Lab, and Fermilab. Europe launched the Quantum Internet Alliance, targeting a multi-node network by 2025. The challenge is distance. Photons carrying entanglement get absorbed by fiber optic cables after about 100 kilometers. You can't amplify them like classical signals because measurement destroys the entanglement. So the networks rely on quantum repeaters, devices that create fresh entangled pairs at intermediate stations and perform entanglement swapping to extend the link. But repeaters need quantum memory, and the best memories today hold coherence for milliseconds, maybe seconds in cryogenic conditions. That's not long enough for continent-scale networks. So the race split into two tracks: fiber networks for cities and satellites for the long jumps. Satellites avoid absorption losses because space is empty. You fire entangled photons through 500 kilometers of vacuum instead of 1,000 kilometers of glass. The technology was supposed to mature in the 2030s. China just demonstrated something that was supposed to be decades away. On August 16, 2016, China launched Mikius, a 620-kilogram satellite carrying a photon source, beam splitters, and detectors sensitive enough to catch single photons from the ground. At 500 kilometers altitude, it generated entangled pairs and beamed them to receiving stations in Delinga and Lijiang, 1,203 kilometers apart. The entanglement survived. Measured correlations exceeded the Bell inequality by 2.37 standard deviations. A year later, Mikius teleported a photon's quantum state from a ground station in Tibet to the satellite as it passed overhead. The fidelity was 0.80, well above the 0.67 threshold that rules out classical explanations. Then it distributed encryption keys between Beijing and Vienna, a 7,600 kilometers link, and hosted the first intercontinental quantum-secured video call. The bitrate was only 10 bits per second. Atmospheric turbulence scattered most of the photons, but the protocol worked. Western programs had barely left the planning stage, and China was already encrypting government communications with entanglement distributed from orbit. In 2020, they launched a second satellite. In 2022, they integrated Mikius into the ground-based network, creating the first hybrid quantum internet spanning space and fiber. The satellite proved that quantum encryption is no longer theoretical, it's operational. When you send a message using quantum key distribution, the encryption key is encoded in entangled photons. If anyone tries to intercept those photons, they have to measure them, and measurement collapses the quantum state, leaving visible traces in the data stream. It's not security by obscurity or computational hardness. It's guaranteed by the Heisenberg uncertainty principle itself. The eavesdropper physically can't extract information without announcing their presence. Banks, governments, and data centers are already deploying QKD links for exactly this reason. China's commercial quantum network now covers 4,600 kilometers across multiple cities, transmitting financial transactions and state communications. Switzerland built a QKD backbone connecting government offices. In 2023, a hospital in Poland used quantum encryption to protect patient records during transfer. The tech isn't coming, it's here. But there's a problem. The current quantum internet can't do the one thing the internet is for. Classical fiber repeaters work by reading the signal, copying it, amplifying it, and sending it onward. Every 80 kilometers or so, your Netflix stream gets cloned and boosted. It's why you can stream from across an ocean. Quantum states can't be copied. The no-cloning theorem, proven in 1982, says if you try to duplicate an unknown quantum state, you'll destroy the original. So you can't just amplify entangled photons the way you amplify light. After about 100 kilometers in fiber, photon loss makes the connection useless. Mikius solved this by shooting photons through near vacuum at altitude, where loss is lower. But you can't build a global network on satellite passes. You need ground infrastructure. And ground infrastructure means repeaters that can extend entanglement without measuring it, without copying it, without collapsing it. The breakthrough came from rethinking what a repeater actually has to do. A quantum repeater doesn't copy the state, it stores it. You entangle photons between nodes A and B, then B and C. The repeater at node B holds both entangled states in quantum memory, performs an entanglement swap, and now A and C are entangled, even though they never directly interacted. Quantum memory devices trap photons or transfer their states into atoms that can hold superposition for milliseconds, sometimes seconds. Researchers use rare earth ions doped into crystals, rubidium vapor cells, and trapped calcium ions. In 2021, a team at Delft University demonstrated entanglement swapping across 3 nodes with memory storage times exceeding 1 second. China's national plan calls for quantum repeaters every 100 kilometers by 2030. A prototype network in Hefei already uses atomic frequency comb memory to store entangled states. Europe's Quantum Internet Alliance is testing erbium-doped crystals that can interface directly with telecom fiber. The pieces are assembling. Even with working repeaters, the quantum internet faces a threat that has nothing to do with technology. In 1994, Peter Shor proved that a sufficiently powerful quantum computer could factor large numbers exponentially faster than any classical machine. That single algorithm makes RSA encryption, the backbone of internet security, obsolete. Every HTTPS connection, every encrypted email, every VPN tunnel relies on the assumption that factoring a 2048-bit number takes longer than the age of the universe. A quantum computer with a few thousand logical qubits could crack it in hours. The math protecting your bank account, your medical records, your government's classified communications collapses the moment that threshold is crossed. And here's the nightmare. Adversaries don't need to wait. They're recording encrypted internet traffic right now, storing terabytes of data they can't read yet. It's called harvest now, decrypt later. In 10 or 15 years, when quantum computers mature, every conversation you thought was private, every document you thought was secure, becomes readable retroactively. The encryption protecting today's secrets has an expiration date. Intelligence agencies are already harvesting encrypted traffic in anticipation of that moment. In 2016, NIST launched a global competition to find encryption algorithms that could resist quantum attacks. Not quantum encryption, classical math designed to be hard even for machines exploiting superposition. 82 proposals entered. By 2024, 4 algorithms were standardized. Crystal's dilithium for digital signatures, Falcon and Sphinx Plus as backups. The urgency is real. The U.S. Quantum Computing Cybersecurity Preparedness Act mandates federal agencies migrate to post-quantum cryptography by 2035. Google began deploying hybrid encryption in Chrome in 2023, layering quantum-resistant algorithms over existing protocols. Apple followed in iMessage. The transition is already underway, a race to armor the internet before the tools to crack it arrive. But there's a catch. These algorithms are based on hard math problems, lattice structures, hash functions, problems we think are hard for quantum computers. We don't have proof. Shor's algorithm blindsided the cryptographic community because no one saw it coming. A future breakthrough could render post-quantum cryptography just as vulnerable as RSA. But even quantum-safe encryption can't protect against a quantum computer's strangest capability. Quantum machine learning uses entanglement to represent data in exponentially larger spaces. A classical neural network processing 300 features needs 300 states to explore every possibility, more than atoms in the universe. A quantum system with 300 qubits holds all those states simultaneously, in superposition, weighting them, interfering them, collapsing to the pattern with the highest probability. In 2019, researchers at IBM trained a quantum neural network to classify handwritten digits using only 2 qubits. It wasn't faster, but it worked with a fundamentally different geometry, mapping data into Hilbert space where distances and angles have no classical analog. Algorithms like quantum support vector machines and variational classifiers exploit this, finding boundaries in feature spaces no classical computer can efficiently search. Google's 2020 results showed a quantum model learning molecular structures 100 times faster than classical equivalents in simulation. Not because of raw speed, but because entangled qubits naturally encode correlations that classical bits have to brute force. The math is still emerging, but the architecture is clear. Quantum machine learning doesn't just accelerate existing models, it accesses patterns classical systems can't see. The first real-world application wasn't optimization or cryptography, it was chemistry. In 2020, IBM used a 28-qubit processor to simulate lithium hydride, a molecule with 4 atoms. The simulation took 3 hours and matched lab results to within 2%. Classical supercomputers can do this too, but they treat electrons as probabilities smeared across space. A quantum computer represents them as actual superpositions, the same way nature does. Pharmaceutical companies started lining up. Merck partnered with Zapata to model protein folding. Roche invested $100 in quantum drug discovery. The pitch was irresistible. If you want to understand how a molecule behaves, use a machine that's already a molecule. But the math scales brutally. A caffeine molecule needs 95 qubits to simulate perfectly. An aspirin molecule, 280. A single enzyme in your bloodstream, over 10,000. Hemoglobin, the protein that carries oxygen through your veins, would require more qubits than there are atoms in the observable universe. But to simulate a single protein accurately, we'd need more qubits than atoms in the universe, unless there's a shortcut. The shortcut is called the variational quantum eigensolver, and it cheats. Instead of running the full simulation on a quantum computer, you run a shallow circuit, measure the result, send it to a classical computer, adjust the parameters, and loop. It's a hybrid. The quantum part handles the entanglement. The classical part handles the optimization. In 2021, researchers at Google simulated a chemical reaction using only 12 qubits and 72 variational iterations. The circuit depth was 12 gates, shallow enough that noise didn't destroy coherence. The result matched experiment. No classical algorithm could compute it faster, but the margin was thin, seconds against minutes. These algorithms don't solve the problem exactly. They approximate. You trade precision for feasibility, and you accept that the answer is only as good as your classical optimizer and your quantum hardware's noise floor. It's pragmatic, not elegant. The question of advantage became urgent when Google made a stunning claim. In October 2019, Google announced that their 53-qubit Sycamore processor solved a random sampling task in 200 seconds that would take a classical supercomputer 10,000 years. They called it quantum supremacy. The paper hit Nature. The headlines went global. IBM responded within 48 hours. Their researchers published a counter-analysis showing the same task could be simulated on a classical system in 2.5 days using clever disk storage tricks. Google's estimate assumed the classical machine would hold everything in RAM. IBM's didn't. The supremacy claim shrank from millennia to hours. The debate fractured into definitions. Was supremacy about any quantum speedup or only speedups on useful tasks? Google's problem was synthetic, designed to be hard for classical computers but pointless in practice. Researchers started using the term quantum advantage instead, but the threshold stayed vague. While researchers argued about benchmarks, a Chinese team quietly built something more powerful. In December 2021, the University of Science and Technology of China announced Zhuchongji 2.1. The 66-qubit superconducting processor tackled a random circuit sampling problem in 1.2 hours. The best classical algorithm they could find would need 8 years on the world's fastest supercomputer. The gap was 10 million times wider than Google's claim, and the task was less ambiguous. Zhuchongji used a lattice of tunable couplers and fast gates, pushing fidelity above 99.5% for single-qubit operations. By 2022, they scaled to 113 qubits, extending the lead even further. IBM fired back with a 127-qubit Eagle processor, then a 433-qubit Osprey. Each machine set new records for coherence and gate speed. The numbers kept climbing, but the tasks remained synthetic, mathematical puzzles with no application outside the lab. But none of these demonstrations solved a problem anyone actually cared about, until now. In 2023, researchers at Quantinuum used a 32-qubit trapped ion system to optimize delivery routes for a logistics company. The quantum algorithm found solutions 12% better than classical heuristics, shaving thousands of dollars off fuel costs per quarter. It wasn't a million times faster, but it was real money. A team at JP Morgan ran portfolio optimization on IBM's hardware, balancing risk and return across 50 assets. The quantum approach converged in 200 iterations, where classical methods needed 800. Materials scientists used variational circuits to predict molecular binding energies for battery cathodes, cutting simulation time from 3 weeks to 4 days. These weren't toy problems. They were production tasks with measurable payoffs. The speedups were modest, sometimes barely 2x, but they appeared in domains where even small improvements translate to competitive edges. The advantage is real but fragile. It vanishes the moment decoherence sets in. Every quantum processor is fighting the same war. Superconducting qubits sit in dilution refrigerators at 15 millikelvin, shielded by layers of copper and lead to block magnetic fields. Trapped ions float in ultra-high vacuum chambers, isolated from vibration and stray electric fields. Coherence times crept from microseconds to milliseconds, then past 10 seconds for some ion qubits. Error-correcting codes turned single fragile qubits into logical qubits protected by redundancy. The surface code, the most popular scheme, needs about 1,000 physical qubits to make one logical qubit that can survive long computations. That's a brutal overhead, but it works. Microsoft and others are chasing topological qubits, exotic states where information is encoded in braided paths that decoherence can't unravel. Cryogenic engineers redesigned every component, hunting sources of noise. Microwave lines, readout circuits, even the control electronics inject heat and interference. Each improvement bought a few more microseconds, a few more gates before the state collapses. One approach doesn't fight decoherence. It embraces it as a feature. Measurement-based quantum computing flips the script entirely. Instead of building a circuit gate by gate, you prepare one giant entangled state at the beginning, then perform measurements in a carefully chosen sequence. Each measurement collapses part of the state, and those outcomes steer the next measurement. The computation isn't in the gates anymore. It's in the pattern of collapse itself. You're not preserving coherence through 100 operations. You're using decoherence as the computational step, extracting classical information from quantum superpositions in a specific order that encodes the algorithm. Robert Rausendorf and Hans Briegel proposed this in 2001, showing that a universal quantum computer could run entirely on single-qubit measurements if you started with the right resource state. No 2-qubit gates during computation, no need to keep qubits isolated for long stretches. Just measure, measure, measure. The catch is obvious. The resource state required is so entangled it might be impossible to create, except nature already did. Cluster states are lattices of qubits where every qubit is entangled with its neighbors in a specific way. Picture a grid where each node connects to the ones adjacent, not through wires, but through controlled phase gates that build correlations across the entire structure. A 2D cluster state with a few hundred qubits becomes a universal resource. Measure them in the right order, and you can run any quantum algorithm. Photons are ideal carriers for this. They don't decohere easily, they travel at light speed, and measuring them is straightforward. You can entangle photons into cluster states using beam splitters and phase shifters, routing them through optical circuits etched onto chips smaller than a fingernail. Xanadu and PsiQuantum are building photonic machines around this model. Their architectures avoid the cryogenic complexity of superconducting qubits, operating at room temperature with off-the-shelf telecom components. The math says a 1 million qubit cluster state could factor RSA 2048 in hours. But creating these states requires a precision that quantum mechanics itself seems designed to prevent. Photon sources are probabilistic. Fire a laser into a nonlinear crystal, and maybe you get a pair of entangled photons, maybe you get none, maybe you get 4 when you needed 2. Fusion gates that join small clusters into bigger ones fail 50% of the time. Each failure cascades. To build a 10,000 qubit cluster, you might need 10 attempts, and each attempt costs microseconds. Current systems achieve cluster state fidelities around 88%. Fault-tolerant measurement-based computation needs 99.9%. The gap isn't a matter of better lasers or cleaner optics. It's photon loss, detector inefficiency, and the fundamental noise floor of the components. PsiQuantum's roadmap banks on improving fusion gate success rates to 99%, which would require detectors that don't exist yet and error rates 100 times lower than state-of-the-art. Labs in China, Germany, and Austria have demonstrated small cluster states with 10 to 20 qubits, enough to prove the concept. Scaling to millions hits a wall where the time to generate the resource state exceeds the time the first qubits remain coherent. You're building a sandcastle while the tide comes in. Yet one research group claims they've found a loophole in the laws of entanglement itself. The loophole is entanglement distillation, a protocol first described by Charles Bennett in 1996. You start with dozens of weak, noisy, entangled pairs shared between two labs. Each pair is corrupted by decoherence, maybe only 70% entangled. Then you perform local measurements on subsets of those pairs, comparing results over a classical channel. The measurements project the remaining pairs into a smaller set with higher fidelity. You've sacrificed quantity for quality, concentrating the entanglement like refining ore into metal. A 2001 experiment at Innsbruck took 4 photon pairs at 75% fidelity and distilled them into one pair at 87%. The process is irreversible. Once you measure, the discarded pairs are gone. Repeat the protocol and you can push fidelity above 99%, high enough for quantum teleportation or error correction. But the yield drops exponentially. Purifying 100 noisy pairs might give you 8 good ones. Purifying those 8 gives you one nearly perfect pair. The math is governed by entanglement measures that quantify how much quantum correlation survives in a mixed state. You can't distill forever. At some threshold, the noise is too high and the protocol fails, yielding 0 pairs no matter how many you feed in. The limits are set by a quantity that determines whether entanglement can exist at all. That quantity is called negativity, and it emerges from a test called the Perez-Horodecki criterion, published in 1996. Take the density matrix describing your quantum state and perform a partial transpose, flipping the indices on one subsystem. If the state is separable, meaning it's just classical correlations dressed up in quantum notation, the result stays a valid probability distribution. But if the state is truly entangled, the partial transpose develops negative eigenvalues, negative probabilities. That's impossible in classical physics, so the appearance of negativity is a smoking gun for entanglement. The PPT test, positive partial transpose, is necessary and sufficient for detecting entanglement in 2x2 and 2x3 dimensional systems. For larger systems, it's necessary but not sufficient, meaning some entangled states slip through. The negativity measure sums those negative eigenvalues into a single number. A maximally entangled Bell pair has negativity 0.5. A separable state has negativity 0. Distillation protocols can increase negativity by discarding low negativity pairs, but the total negativity across all pairs never increases. It's a conserved resource, like energy in a closed system. In 2002, researchers proved that negativity is monotonic under local operations and classical communication, the same restrictions that govern distillation. You can't create negativity from nothing using local measurements. These measures suggest entanglement obeys laws eerily similar to the second law of thermodynamics. The parallel is exact. In thermodynamics, entropy measures disorder, and the second law says it never decreases in a closed system. In entanglement theory, entanglement entropy measures quantum correlation, and it never increases under local operations. Distillation is a refrigeration cycle. You extract pure entanglement by dumping noise into the environment, raising the total entropy. There's even an entanglement analog of temperature. States with high entanglement are cold, states with low entanglement are hot. Protocols that convert entangled pairs into work, like superdense coding or teleportation, are heat engines. The efficiency is bounded by an equation identical to Carnot's limit, with entanglement entropy replacing thermal entropy. In 2008, physicist Michał Horodecki and colleagues formalized this as the laws of entanglement thermodynamics. The zeroth law: maximally entangled states are the coldest possible, analogous to absolute zero. The first law, entanglement is conserved in reversible protocols. The second law, irreversible protocols always destroy some entanglement. There's even a third law stating you can't reach perfect entanglement in finite steps. The framework isn't just metaphor. Experiments have measured entanglement heat capacity, the amount of noise required to degrade a quantum state by 1 bit of correlation. A 2015 test at ETH Zurich confirmed the predictions to within 2%. If entanglement is a thermodynamic resource, then quantum computers are heat engines running on correlation. In 1961, IBM physicist Rolf Landauer proved something disturbing. Every time you delete a bit of information, you must dissipate at least kT ln 2 joules of heat into the environment. At room temperature, that's 3 times 10⁻21 joules per bit. It sounds tiny, but it's a hard thermodynamic flaw. Your laptop can't erase data without paying this price in heat. The principle links information theory to the second law of thermodynamics, making information as physical as mass or charge. For 50 years, researchers assumed quantum information followed the same rule. A 2011 experiment at the University of Tokyo measured the heat from erasing a single bit stored in a quantum dot. They found the expected Landauer limit, give or take experimental noise. But in 2018, a team at Oxford tried erasing entangled qubits instead of independent bits. The measurements showed negative heat dissipation in 14% of trials. Erasing entanglement turns out to release energy that shouldn't exist according to classical thermodynamics. Maxwell's demon was a thought experiment from 1867. An intelligent being sorts hot and cold molecules through a door, extracting work from a gas that should be at equilibrium. It violates the second law unless the demon's memory also costs entropy. Entangled particles can play the demon's role without violating anything. In 2017, researchers at the University of Campinas used pairs of entangled photons to extract 2.4 times 10⁻20 joules from a thermal reservoir. A classical observer sees equilibrium, but the quantum correlations reveal a hidden energy gradient. The experiment worked because entanglement provides information the environment doesn't have access to. You can measure one photon, collapse the pair, and use the correlation to do work. The entropy increase happens in the entangled system, not the reservoir. But here's the problem. If you can extract work from entanglement, and erasing entanglement releases energy, where does that energy come from in the first place? The resolution requires accepting that information has weight, literally. In 2019, physicist Melvin Vopson published calculations suggesting that a bit of information at room temperature contributes 3.19 times 10⁻38 kilograms to a system's mass via E equals -2. A 1 terabyte hard drive would be 2.5 times 10⁻25 kilograms heavier when full than when empty. It's far below any scale we can measure, but the principle is testable. A proposed experiment at the University of Portsmouth would trap ultra-cold atoms in an optical lattice, encode information in their spin states, then measure gravitational effects with atom interferometry. The target sensitivity is 10⁻30 kilograms. If information has mass, the implications cascade into foundational physics. A black hole's event horizon encodes information in its area, and that information would contribute to the hole's total mass. Deleting a bit would release 2.87 times 10⁻21 joules and reduce the system's mass by 3.19 times 10⁻38 kilograms. The math is consistent, but nobody's proven it experimentally. The Portsmouth experiment is scheduled for 2027, assuming they can isolate the setup from seismic noise and thermal drift. If information has mass, then entangled particles should exert a gravitational attraction that depends on their quantum state. That Portsmouth setup assumes gravity is just the backdrop. But what if gravity itself can create entanglement? The idea is simple. Take two masses, isolate them from everything, and let them interact through gravity alone. If their quantum states become correlated without touching, without photons, without anything but space-time curvature, then gravity isn't classical, it's quantum. The protocol was sketched out in 2017. You need two microspheres, maybe 10⁻14 kilograms each, separated by millimeters. Cool them to their quantum ground state so thermal noise doesn't drown the signal. Then measure whether their positions are entangled after they've orbited each other gravitationally for a few seconds. The signal you're looking for is tiny. Gravitational coupling at that scale is 10⁻44 times weaker than electromagnetism. You're trying to detect a phase shift smaller than the wavelength of the particle's wave function, accumulated over seconds. Every stray photon, every passing cosmic ray, every vibration in the lab floor destroys coherence. The experiment requires equipment so sensitive it could detect the gravitational pull of a bacterium. The team at Karolinska proposed a workaround in 2019. Instead of microspheres, use two superconducting masses shaped like dumbbells, each 14 micrograms, levitated by magnetic traps inside a dilution refrigerator at 20 millikelvin. The dumbbells oscillate at 100 Hz. You tune their frequencies so they resonate through gravitational interaction. After 500 seconds, you measure both masses in superposition. If gravity is classical, the measurements are independent. If gravity is quantum, you see correlations that violate a Bell inequality. The signature is a 3 sigma deviation in the joint probability distribution, detectable only if you can keep both masses coherent for 8 minutes. That coherence time is the killer. At 20 millikelvin, blackbody radiation is still around. The magnetic traps leak flux. Seismic noise from traffic 2 kilometers away shows up in the accelerometer data. The proposal calls for active feedback, real-time quantum state estimation, and a vacuum better than 10⁻17 torr. Nobody's built a system like that. If it succeeds, it would prove that space-time itself is entangled at the Planck scale. The Planck scale is where quantum mechanics and general relativity collide. At 10⁻³ meters, space-time isn't smooth. It's a foam of virtual particles popping in and out of existence, each pair borrowing energy from the vacuum for 10⁻⁴ cube seconds. Those pairs are entangled. They have to be, because they're created from the same quantum event. Wheeler called it quantum foam in 1955. The math suggests space-time at that scale is a seething network of entanglement, constantly forming and breaking as virtual particles annihilate. Every point in space is connected to every other point through these fleeting correlations. Non-locality isn't a bug, it's the foundation. This affects everything. If space-time is fundamentally non-local, then the speed of light isn't the deepest limit. Information can be correlated across distances instantly, not by traveling faster than light, but because those distances are built from entanglement in the first place. The geometry we see is emergent, a large-scale average over quantum correlations at the Planck scale. This foam might be why black holes radiate and why information can't be destroyed. When Hawking first calculated it in 1974, the radiation seemed thermal, random photons carrying no information about what fell in. But if the radiation is truly random, the information is gone forever, and quantum mechanics breaks. The resolution came from entanglement. Each particle of Hawking radiation isn't independent. It's entangled with every particle emitted before it, forming a chain that stretches back to the black hole's formation. That chain encodes the information in correlations too subtle to see in any single photon. An observer catching the radiation over billions of years could, in principle, reconstruct what fell in by measuring the entanglement structure. Not the particles themselves, but the pattern of how they're linked. The information never left. It was always there, hidden in the quantum correlations. But there's a cost. The radiation is also entangled with the black hole's interior, with the partner particles that fell past the horizon. The mechanism requires accepting that black hole interiors and exteriors are quantum Xerox copies, simultaneously. Leonard Susskind called it complementarity. An astronaut falling through the event horizon sees nothing special. No barrier, no wall, just smooth space-time all the way down. But a distant observer watching from outside sees the astronaut's information smeared across the horizon, encoded in Hawking radiation. Both descriptions are correct. Both are complete within their own reference frame. The contradiction only appears if you try to compare them directly, which relativity forbids. You can't be in both places at once. Entanglement enforces the boundary. The infalling observer's reality and the exterior observer's reality are complementary facets of the same quantum state. It's observer-dependent physics taken to its limit. Not just velocities or simultaneity, but the structure of space-time itself depends on where you are and what you measure. The black hole interior exists for the infalling observer. It doesn't exist, in the same sense, for the distant one. The resolution held for 20 years. Then the math tightened. But in 2012, 4 physicists showed that complementarity leads to an impossible choice. Almheri, Marolf, Polchinski, and Sully ran the numbers on old Hawking radiation. After a black hole has evaporated past half its original mass, the early radiation is maximally entangled with the late radiation. Every qubit outside is paired with another qubit outside. But complementarity says that late radiation must also be entangled with its partner inside the black hole, the particle that fell past the horizon. Monogamy of entanglement forbids this. A qubit can't be maximally entangled with 2 different systems. One of those entanglements has to break. If you preserve the interior entanglement, information is lost and quantum mechanics fails. If you preserve the exterior entanglement to save information, the interior partner vanishes. The vacuum at the horizon tears apart. An infalling observer hits a wall of high-energy particles, a firewall, and burns before crossing. The equivalence principle says free fall is indistinguishable from floating in empty space. A firewall violates that. Resolving the firewall requires abandoning either locality, quantum mechanics, or the equivalence principle. In 2013, Juan Maldacena and Leonard Susskind published a paper with a strange title, ER equals EPR. ER stands for Einstein-Rosen bridges, the technical name for wormholes. EPR stands for Einstein-Podolsky-Rosen, the 1935 paper that described entanglement. The equals sign wasn't metaphorical. They proposed that every pair of entangled particles is connected by a wormhole. Not a traversable one, you can't send information through it, but geometrically, entanglement and wormholes are the same phenomenon. When you entangle 2 electrons, you're stitching a tiny bridge through spacetime between them. The firewall paradox vanished. An observer falling into a black hole stays connected to Hawking radiation through microscopic wormholes threading the event horizon. No firewall, no contradiction, but the cost was enormous. If they're right, then spacetime isn't fundamental. It's woven from entanglement. The IT from qubit collaboration spent years working out the implications. They started with a simple quantum system with no geometry at all, just qubits in superposition. Then they entangled them in specific patterns. Distance emerged. Geometry appeared where none existed before. In their models, 2 regions of space are close together if the qubits describing them share lots of entanglement. Cut the entanglement, and the regions drift apart. Space itself is a map of quantum correlations. The smooth continuum Einstein described is an approximation, a blurred average over trillions of entangled degrees of freedom. They found something stranger. Change the entanglement pattern, and you change the shape of space. Increase entanglement between distant qubits, and you can connect regions that were causally separated. The number of dimensions isn't fixed either. It depends on how information is distributed. The mathematics predicts something impossible. The universe's geometry depends on what you know. In 2014, physicists noticed that ADS-CFT holography and quantum error correcting codes have identical mathematical structure. The bulk geometry, the interior 3D space, is encoded redundantly in boundary entanglement. You can erase part of the boundary and still reconstruct the interior, exactly like a quantum error correction algorithm recovering data from damaged qubits. Black holes are quantum codes. Wormholes are entanglement-assisted teleportation protocols. The holographic principle isn't just a storage trick. It's the universe protecting information from decoherence. Every region of space is error-corrected by the entanglement structure around it. Daniel Harlow and John Preskill proved that certain geometric properties of spacetime, like the fact that you can't have closed time-like curves, follow directly from quantum error correction. The laws of physics we observe aren't fundamental, they're consequences of the code. This means the universe might be a self-correcting quantum computer, and we're subroutines running inside it. In 2002, physicist Seth Lloyd calculated the computational capacity of the observable universe. Using quantum information theory, he arrived at 10^-120 operations performed on 10^-90 bits since the Big Bang. That's not a metaphor. Those are hard limits derived from the speed of light, the Planck constant, and the age of the cosmos. Every black hole has an entropy proportional to its surface area, not its volume. A sphere with radius r can only store 1 bit per 4 Planck areas on its boundary. The holographic principle says the same constraint applies everywhere. The 3D universe you experience might be a projection of 2D information encoded on a distant boundary. Quantum field theory gives the same answer. When you try to probe distances smaller than the Planck length, 1.6 times 10⁻35 meters, the energy density becomes so extreme you create a black hole. Space itself has a resolution limit, like pixels on a screen. Below that scale, the concept of distance stops meaning anything. This isn't about us living in a simulation. It's deeper. The universe obeys computational rules because information processing has physical costs, and those costs are baked into the structure of spacetime. But if the universe is computational, then who's running the program? The cosmic microwave background, the afterglow of the Big Bang, shows a temperature uniformity of 1 part in 100,000 across the entire sky. Regions separated by 26 billion light-years have identical temperatures, yet they've never been in causal contact. Standard inflation explains this by saying the universe expanded faster than light, bringing distant patches into thermal equilibrium before they separated. But in 2005, physicists realized inflation alone isn't enough. The CMB's correlations are too perfect, too finely tuned. If the early universe was a quantum state, it must have been maximally entangled across cosmological distances. Every photon we detect today carries information about the entanglement structure 380,000 years after the Big Bang. The Planck satellite found anomalies in the CMB's power spectrum at large angular scales. One interpretation is that we're seeing evidence of primordial entanglement between our observable patch and regions beyond the cosmic horizon. The universe's initial state wasn't random. It was a carefully prepared quantum superposition. Dark energy, which makes up 68% of the universe, might be entanglement energy. As space expands, quantum correlations stretch across larger distances, creating a negative pressure that accelerates cosmic expansion. The entanglement pattern we see might be the only one compatible with observers existing to measure it. Eternal inflation says the Big Bang wasn't a single event. It's happening continuously, forever, in an infinite fractal structure. Quantum fluctuations create bubble universes that nucleate and expand. each with different physical constants, different numbers of dimensions, different laws. Our universe is one bubble in an endless foam. Combine that with the many worlds interpretation, every quantum measurement doesn't just create branches in our universe, it creates branches across the entire multiverse. When a particle decays here, it doesn't decay in 10^500 other bubbles. Each possibility is realized somewhere, and they're all connected by entanglement, threading through the multiverse. The anthropic principle says we observe the physical constants we do because we couldn't exist otherwise. If the electromagnetic force were 4% stronger, stars wouldn't fuse carbon. If the cosmological constant were larger by 1 part in 10^120, galaxies wouldn't form. The multiverse explains this by brute force. Every possible universe exists. We're in one that allows chemistry and biology. But here's the problem. If every quantum outcome happens, if every possible universe exists, then probability stops working. You can't calculate likelihoods when everything is equally real. Physicists call this the measure problem, and after 40 years, there's no solution. But there's one interpretation that makes all the others irrelevant, and it's unfalsifiable. In 1981, Alan Guth proposed eternal inflation. The Big Bang didn't happen once. It's still happening, everywhere, forever. Quantum fluctuations in the inflaton field spawn new universes at a rate faster than space can expand between them. Each bubble is causally disconnected from the others. Inside one bubble, the electron has a mass of 9.1 times 10⁻31 kilograms. Inside another, it's 43 times heavier, and atoms can't form. In a third, electromagnetism is weaker by a factor of 1020, and stars burn for trillions of years. The landscape of string theory predicts 10^500 possible vacuum states, each one a universe with different physics. Most are sterile. A handful support complexity. We're in one of them, not because we're special, but because we couldn't exist anywhere else. The bubbles expand into each other, colliding at light speed. When they touch, the collision leaves a disc-shaped pattern in the fabric of space-time itself, a bruise written into the cosmic microwave background. But there's one experiment that claims to have found the scar. In 2007, astronomers discovered the CMB cold spot. It's a region 1.8 billion light-years across, where the temperature is 70 microkelvin colder than the surrounding sky. Standard inflationary models predict fluctuations this large occur with a probability of less than 1 in 50. In 2010, Laura Mersini-Houghton analyzed the cold spot's profile. She found a disc-like pattern consistent with a bubble collision during inflation, 13.8 billion years ago. The void would have compressed our universe's expansion in that direction, cooling the radiation we see today. The Planck satellite confirmed the anomaly in 2013, measuring it at 5.9 sigma significance in one analysis. But other teams argued it's a supervoid, a 1.3 billion light-year empty region 3 billion light-years away, red-shifting photons as they cross it through the integrated Sachs-Wolf effect. Either explanation works mathematically, a collision scar or a statistical fluke amplified by voids. We can't rerun the universe to check. The debate remains open, the data ambiguous, the implications staggering if true. The problem is that the math predicts we shouldn't exist at all. Eternal inflation creates infinite universes. Most have physics hostile to life, but infinity times any non-zero probability equals infinity. There are infinite universes where you exist, infinite where you don't, infinite where Earth formed 10 seconds ago, with fake memories already in place. How do you calculate the odds of measuring a cosmological constant of 10⁻122 when there are infinitely many observers in universes with that value, and infinitely many in universes without it? You can't divide infinity by infinity. The Bohr rule, the foundation of quantum probability, collapses. Physicists tried every trick: finite cutoffs, geometric weighting schemes, counting by volume, by observer moments, by entropy. Every method gives a different answer. In some measures, we're typical. In others, we're in the least probable universe allowed by the anthropic principle. André Linde calls it the worst problem in cosmology. Max Tegmark calls it a crisis for science itself. If we can't predict which universe we should observe, the multiverse becomes unfalsifiable. A story that explains everything explains nothing. And that's when physicists realized entanglement might be the only thing holding reality together. Here's what we know. Every photon that bounced off your hand and hit this screen was once entangled with particles in a star that died 4 billion years ago. Every atom in your body interacted with others during the Big Bang, creating links that persist across 13.8 billion years. The universe isn't made of isolated objects. It's a single, unbroken web. Physicists call it the entanglement horizon. When two particles interact, they share a quantum state. That state doesn't vanish when they separate, it spreads. A photon from the sun entangles with an electron in your retina. That electron was already entangled with others in your DNA. The web grows with every collision, every measurement, every moment. By some estimates, a single particle in your brain is quantum correlated with 10 to the 23rd other particles across the observable universe. The cosmic microwave background, the leftover light from the Big Bang, is entangled with every atom that ever absorbed it. We're not separate from the cosmos. We're woven into it at the most fundamental level. But in 2022, a team discovered something that changed everything we thought we knew. Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize in Physics for experiments that closed the final loopholes. They proved entanglement violates local realism. Local realism is the idea that objects have definite properties independent of observation, and that influences can't travel faster than light. For 50 years, physicists hoped a hidden variable might restore that picture. The Nobel experiments killed it. Zeilinger's team in Vienna entangled photons and measured them 144 kilometers apart, faster than light could travel between the detectors. Aspect's setup in Paris closed the detector loophole by switching measurement angles after the photons were already in flight. Clauser's original work in the 1970s showed correlations that no local hidden variable could explain. Every test gave the same result. The universe is non-local. That means reality doesn't exist in neat, separated chunks. A measurement here instantaneously affects a correlated particle there, not by sending a signal, but by collapsing a shared wave function that was never truly divided by distance. Space doesn't isolate. It's an illusion painted over a deeper structure. And if space is emergent, something we perceive rather than something fundamental, then the order of events might be too. Because if space isn't fundamental, then neither is causality. Retrocausality is the idea that effects can precede their causes. It sounds absurd until you realize quantum mechanics already allows it. The transactional interpretation, proposed by John Cramer in 1986, describes particles exchanging waves forward and backward in time to create the present. The future sends an echo back. The past listens. They meet in what we call now. Experiments hint at this. In 2017, researchers at the Australian National University showed that a photon's path through a double-slit experiment could be altered by a choice made after it had already passed through. The decision came later in time, but the photon behaved as if it knew in advance. Similar tests with entangled particles show correlations that seem to require information traveling backward through the light cone. Yakir Aharonov's weak measurement framework goes further. It suggests quantum systems are influenced by both their past state and their future boundary condition. You're not just shaped by what came before, you're pulled forward by what comes after. The block universe, where past, present, and future exist simultaneously, might not be metaphor. It might be mechanics. The measurement you make tomorrow may have already determined what happened yesterday. Take a single photon and send it toward two slits. Behind them, a detector waits to see which path it took. But there's a twist. You can choose to erase that which path information after the photon has already hit the screen. using entangled partner particles and a set of downstream detectors that scramble the record. When the path information exists, the photon behaves like a particle, no interference. When you erase it, the interference pattern comes back, the wave behavior returns. Nothing strange yet, except the erasing happens after the photon was already detected. The choice comes later, and the photon's earlier behavior matches the choice you hadn't made yet. Physicists have run versions of this since the 1980s, and the pattern holds every time. The photon seems to know, before you decide, how you're going to decide. It's not that information travels backward, it's that the story you tell about the past isn't fixed until you finish measuring. And that brings us to the question no one wants to answer. What exactly counts as a measurement? A wave of possibilities collapses into one definite outcome the moment it's observed. But observed by what? For decades, some of the sharpest minds in physics floated an uncomfortable idea. Maybe it takes a conscious mind to make the collapse happen. Maybe the universe stays fuzzy until something looks. Eugene Wigner, a Nobel laureate, took this seriously. His thought experiment put a friend inside a sealed lab making a measurement and asked whether reality was settled for Wigner outside until he opened the door. Push that far enough and it gets dizzying. If observation creates the outcome, then a rock, a river, a galaxy with no one watching sits in a blur of maybes. It sounds like mysticism dressed up in equations, and most physicists hated it. Because if consciousness is doing the collapsing, then reality depends on us in a way that feels backward, even dangerous. But here's what they discovered when they tried to remove the human from the equation. You don't need a person, you need information. When a quantum system interacts with anything that records its state, a detector, a stray air molecule, a photon of light, the superposition breaks down. Physicists call it decoherence, and it happens in fractions of a nanosecond. Consciousness never enters the picture. Quantum computers made this concrete. Inside them, qubits hold delicate superpositions, and researchers can make one qubit measure another. The measuring qubit collapses its target. No human, no eyeballs, just one piece of quantum hardware observing another. The outcome is definite, recorded, real. Awareness isn't the trigger, interaction is. But something stranger shows up in the data. The measuring qubit doesn't stay separate. It gets entangled with the thing it measured, and then with the next system it touches, and the next. The correlation spreads outward like a stain, linking particle to detector to environment. Nothing is ever truly measured in isolation, so decoherence explains why big objects look solid and classical, but it raises a sharper problem. The question is whether reality itself has a size limit. For decades, physicists have been pushing the boundary. They've put electrons in superposition, then atoms, then molecules. In 2019, a team in Vienna put a molecule made of 2,000 atoms into two places at once. Every year, the objects get bigger. Every year, the line between quantum and classical moves. But nobody knows where it stops, or if it stops at all. Some theorists think there's a hard limit, a fundamental scale where quantum mechanics simply breaks down. Others think it's just engineering, better vacuums, colder temperatures, longer isolation from the environment. The race is to find out which one is true, and the experiments are getting extreme. In 2024, they crossed a line no one thought was possible. A team at MIT took a virus, not a molecule, not a cluster of atoms, but a complete biological structure, 5 × 10⁷ atoms. They cooled it to near absolute zero, trapped it in optical tweezers, and put it into quantum superposition. The virus existed in two states simultaneously, not metaphorically, not in theory. They measured the interference pattern. They confirmed entanglement across its entire structure. This wasn't inert matter anymore. It was a thing that could, in principle, have once been alive, and for a fraction of a second, it occupied two mutually exclusive realities at the same time. The boundary didn't hold. The quantum world reached into ours. Because if a virus can be in two states at once, what about you? You are made of particles. Every atom in your body obeys quantum mechanics. Your electrons don't have definite positions until something measures them. Your molecules are entangled with the environment, with the air, with the light bouncing off your skin. So what are you when no one is looking? Do you have a definite shape, a definite location, a definite state? Or are you smeared across a cloud of possibilities, collapsing into one configuration only when the universe forces a measurement? Some interpretations say you're always definite. Decoherence makes you classical, even if no conscious observer is watching. But that doesn't solve the problem. It just moves it. Because decoherence is entanglement with the environment, and entanglement doesn't collapse the wave function, it spreads it, which means the universe itself might be in superposition, branching with every interaction, and you're just a pattern that thinks it's singular. There's one last possibility, and it's the one most physicists refuse to talk about. In 1987, physicist Hans Moravec proposed a thought experiment called quantum suicide. You're strapped to a machine connected to a quantum trigger. It measures a particle's spin. Spin up, you live. Spin down, you die instantly. In the many worlds interpretation, each measurement splits the universe. From your perspective, you only experience the branches where you survive. The universe where you died continues without you, but you never experience it. You keep surviving, iteration after iteration, in an increasingly improbable chain of worlds. This isn't about cheating death. It's about what entanglement and superposition actually mean for experience itself. If the wave function never collapses and reality just branches, then your subjective continuity always follows the path where you exist. You can't witness your own non-existence. Other observers see you die in some branches. But you, the pattern reading this right now, only ever travel forward through branches where observation continues. That's the cold resolution. If entanglement is real and many worlds is correct, you're immortal to yourself, always disappearing into someone else's history. So what does this mean for everything you thought was real? Reality is non-local. A measurement here changes the outcome there, faster than light could ever travel between them. Einstein's 1935 objection was correct. Quantum mechanics defies local realism. What he didn't predict was that nature would choose quantum mechanics. Time might not be fundamental. John Wheeler's delayed choice experiments showed that present measurements affect past states. Retrocausality isn't science fiction anymore. It's sitting in peer-reviewed journals, replicated in labs from Vienna to Beijing. Observation creates outcomes. Before measurement, particles exist in superposition, all possibilities at once. The act of looking forces a choice. The universe doesn't have answers until you ask the question. Wojciech Zurek's quantum Darwinism suggests reality is information that survived observation, selected by decoherence into stable classical states. The world you touch, the chair you sit in, the screen you're reading, all of it is a web of entangled information with no objective existence outside measurement. Science didn't discover reality, it dismantled it. And we're only just beginning to understand what we've broken. In 1935, Einstein wrote a paper trying to prove quantum mechanics was incomplete. By 1964, John Bell showed how to test it. By 1982, Alain Aspect's lab in Paris confirmed entanglement was real. In 2022, Aspect, Clauser, and Zeilinger won the Nobel Prize for closing every loophole. Today, quantum computers with 1,000+ qubits are coming online, using entanglement as their operating principle. Experiments are scaling up, entangling photons across continents, testing whether gravity collapses wave functions, searching for the boundary where quantum becomes classical. The interpretation question remains unsolved. Copenhagen says measurement collapses the wave. Many worlds says it branches. Pilot wave theory says particles always had positions. Relational quantum mechanics says reality is observer-dependent. all the way down. No experiment has ruled any of them out. But the entanglement is confirmed. The non-locality is real. The universe is weirder than Einstein ever feared, and we're living inside the experiment, running it with every observation we make. Every measurement you make collapses a wave function somewhere. Reality is participatory, whether you wanted it to be or not. So here's where we are. Quantum entanglement has been verified in labs across the world, with particles separated by 1,200 kilometers still correlating instantly. The 2022 Nobel Prize went to physicists who closed the last loopholes, and quantum computers are now exploiting entanglement to solve problems classical machines can't touch. The technology is advancing faster than the philosophy. We're building quantum networks, quantum sensors, quantum encryption systems, all running on a phenomenon we still can't fully explain. The math works, the experiments work, but the why, the how, it doesn't need space or time to connect two particles. That's still open. Einstein called it spooky action at a distance because it violated everything he believed about locality and realism. He was right to be unsettled. The universe doesn't behave the way we thought, and every new experiment confirms it. We're still here, still measuring, still collapsing wave functions with every observation. The philosophical crisis remains unsolved. Reality might be participatory, it might be many worlds, or it might be something we haven't imagined yet. For now, we live in a universe where two particles can share a single state across any distance, where the act of looking changes what we see. If that terrifies you, good, it should. If this broke your brain, there's more where that came from.